Welcome to Audio Sleep Stories for Adults. Amidst the rushing currents of everyday life, there lies a peaceful space, a gentle refuge where profound ideas don soft cloaks of storytelling, inviting your mind to wander as your body unwinds into restful sleep. Tonight, we embark on a journey into the realm of exotic spacetimes, a venture beyond the familiar dimensions that frame our existence, where the very fabric of reality twists and turns in ways both strange and beautiful. Imagine a universe where time folds upon itself like a delicate origami, where wormholes thread through cosmic tapestries, connecting distant galaxies as if they were neighboring towns. Picture a place where black holes don't merely swallow light, but perhaps open doorways to other dimensions. These are not flights of fancy, but ideas born from Einstein's equations, refined by the hands of theoretical physicists, and glimpsed in the patterns of our accelerating cosmos. Have you ever wondered what it means to move not just through space, but through time in ways that defy intuition? Could there be shortcuts through space-time, called closed time-like curves, that twist causality into loops, or realms where gravity behaves differently, reshaping the geometry of everything it touches, giving rise to exotic matter and energy that challenge everything we thought we knew? As you settle into your seat, close your eyes, or simply relax your body, let each word carry you deeper into this landscape, where science blends with wonder, where the boundaries between imagination and reality blur, and where the universe reveals its hidden symmetries and secrets. In minutes, you may drift off gently, like a warm summer breeze brushing over a quiet meadow, or awaken with a new question, a spark ignited within your heart, ready to chase the mysteries of existence. So now, let us begin. Imagine standing on the edge of a cosmic ocean, where waves ripple not with water but with the very fabric of reality itself. Space and time intertwined in a dance so intricate that our everyday intuition falters. Picture, if you will, a place where light bends in ways that defy common sense, where the ticking of a clock might speed up or slow down depending on where you stand, where the geometry of the cosmos warps and twists into shapes that challenge our deepest understanding of existence. This is the realm of exotic spacetimes, a concept that stretches our minds beyond the conventional, inviting us to explore a universe that is not merely vast but fundamentally strange, mysterious, and profoundly beautiful. The story of exotic spacetimes begins not in some distant star system or theoretical cloud of interstellar dust, but rather within the mind of one of the 20th century's most brilliant thinkers, Albert Einstein. His formulation of general relativity in 1915 altered our view of gravity from a mere force to a manifestation of curved spacetime geometry. Suddenly, gravity was geometry. Mass and energy told space how to curve, and spacetime told matter how to move. Yet, Einstein's equations did something even more profound. They allowed for solutions that were as bizarre as they were mathematically consistent, hinting at cosmic possibilities that could challenge the very fabric of reality as we understand it. Among the most tantalizing of these solutions emerged from the minds of physicists probing the edges of Einstein's theory, forms of spacetime that are not just curved but exotic. These aren't your garden-variety black holes or the expanding universe we see in our night sky. Exotic spacetimes include realms where wormholes might bridge vast cosmic distances, where time loops could allow a voyage into the past, or where the topology of space folds in on itself in ways that introduce causality paradoxes and challenge the arrow of time. Picture the Einstein-Rosen bridge, a hypothetical tunnel through spacetime that could, in theory, connect two distant points in the universe, allowing instant travel, a concept that has captivated scientists and science fiction alike. But what is it that makes these spacetimes so exotic? At the heart of it lies the nature of the matter and energy required to sustain such configurations. Unlike the familiar matter and radiation that make up stars, galaxies, and ourselves, exotic spacetimes often demand forms of energy that violate well-established physical principles, such as negative energy density or exotic matter. These hypothetical substances possess properties that seem to defy the energy conditions underpinning classical physics and challenge the very notion of stability and causality. For example, the traversable wormholes studied by physicist Kip Thorne require this kind of exotic matter to keep their throats open, preventing them from collapsing instantaneously under gravitational pressure. This requirement leads us into the realm of the unknown, where quantum field theory, the tentative framework for uniting the physics of the very small with the fabric of spacetime, hints that perhaps such exotic energy distributions might be more than mere speculation. Casimir effect experiments, which measure the vacuum energy between two closely spaced metal plates, reveal that the vacuum of space is not truly empty, but teeming with quantum fluctuations that can lead to negative energy densities in small regions. This experimental insight, while subtle, opens a door to the possibility that the universe's vacuum might, under certain extreme conditions, produce the exotic matter needed to stabilize these remarkable spacetimes. Yet even as we ponder the physics, exotic spacetimes beckon us to deeper philosophical reflection. They invite us to reconsider the nature of time itself. If closed time-like curves, a feature of some exotic solutions like the Gödel metric or Tipler cylinders, permit journeys into the past, what does this mean for causality, free will, and the linear narrative we impose on our lives? The very notion of cause and effect, so foundational to science and human experience alike, comes under questioning. Could the universe be a vast cosmic loom, weaving threads of time that loop back on themselves, blurring the distinction between past, present, and future? Furthermore, the entanglement of spacetime geometry with quantum information in theories like the holographic principle suggests that exotic spacetimes might offer clues about the deepest layers of reality. Recent work connecting the geometry of wormholes to quantum entanglement, captured in the enigmatic phrase equals EPR, coined by physicists Leonard Susskind and Juan Maldacena, suggests that spacetime itself could be emergent from the quantum entanglement of information. Exotic spacetimes, then, are not mere mathematical curiosities, but windows into the quantum underpinnings of the cosmos. Historically, the exploration of exotic spacetimes is a tale woven with moments of profound insight and persistent mystery. Consider the 1935 paper by Einstein and Nathan Rosen, where the concept of bridges in spacetime was first introduced, or the 1988 work by Morris and Thorne that breathed new life into the study of traversable wormholes, transforming them from science fiction dreams into serious theoretical constructs. These milestones represent humanity's courage to dream beyond the comfortable boundaries of established physics and explore the wild landscapes that lie beyond. The cosmic dance of exotic spacetimes also draws us into the question of the limits of scientific knowledge. Can the universe truly allow such phenomena? Or are these mathematical oddities, lurking in the shadowy outskirts of theory, destined to remain abstract curiosities? NASA's exploration of extreme physical environments, such as the Event Horizon Telescope's capture of the shadow of a black hole, grounds us in empirical reality. Yet the direct observation of exotic spacetimes remains elusive. Could future generations unlock the technology to peer into the depths of wormholes or witness the loops of time itself? Or is our current understanding forever bounded by the horizon of what the cosmos allows? In confronting exotic spacetimes, we also confront ourselves, our desire to transcend distance and time, to seek not only knowledge but freedom from the constraints of the here and now. The human imagination soars on the wings of these ideas, inspiring visions of interstellar travel, time exploration, and the ultimate unification of physics. Yet, with these dreams comes a humbling reminder of our smallness in the cosmic arena. The universe may be stranger than we can fully grasp, and exotic spacetimes might be the silent whispers of a reality far richer and more complex than our current senses and intuition permit. As we embark on this journey into the heart of exotic spacetimes, we stand at the confluence of physics, philosophy, and the human spirit, invited to ask not just what the universe is, but what it means to exist within such a strange and wondrous tapestry. Could the mysteries of exotic spacetimes hint at a cosmos where time, space, and matter are but threads in a grander design, ever unfolding beyond our grasp? And if so, what stories might the universe be waiting to tell through the curious geometry of its hidden realms? The nonlinearity and complexity of these equations permit a rich variety of solutions, many of which correspond to well-known physical scenarios, such as the Schwarzschild solution describing a non-rotating, uncharged black hole, or the Friedmann-Lemaitre-Robertson-Walker metric modeling an expanding universe. However, embedded within these solutions lie more exotic configurations, which challenge prevailing physical intuitions. Holds, implying that energy density as measured along any light-like direction is non-negative. Exotic spacetimes often violate these conditions, necessitating negative energy densities or pressures that defy conventional matter fields. This violation is at the heart of the theoretical possibility of constructs like traversable wormholes and warp drives. In the landmark paper by Morris and Thorne, 1988, the authors constructed a model for traversable wormholes that explicitly relies on exotic matter, violating the NEC to maintain an open throat through which signals or travelers could pass safely. Their analysis detailed the spacetime geometry, geodesics, and tidal forces that a hypothetical traveler would experience. Importantly, the stress-energy tensor required negative energy density localized around the wormhole throat, a circumstance that classical forms of matter and energy cannot fulfill. However, quantum field theory introduces nuances that potentially ease these restrictions. Quantum phenomena like the Casimir effect showcase measurable negative energy densities in vacuum states confined between conducting plates, a result of imposing boundary conditions on quantum fields. Ford and Roman, 1995, explored quantum inequalities that place stringent limits on the magnitude and duration of negative energy densities, thus constraining the scale and stability of exotic structures. These inequalities suggest that while negative energy is fundamentally permitted in quantum settings, its presence is fleeting and minuscule under ordinary circumstances. Nevertheless, these findings hint that exotic spacetimes might not be mere mathematical abstractions, but could, in principle, manifest under extreme or engineered quantum conditions. Beyond the wormholes, other exotic spacetime solutions introduce even more provocative features. The Gödel metric, discovered by Kurt Gödel in 1949, describes a rotating universe with closed time-like curves, CTCs, that permit paths returning to their own past, theoretically enabling time travel. Though this cosmological solution is unphysical as a model of our universe, due to its matter content and rotation, it serves as a critical example illustrating how solutions to Einstein's equations can allow causality violations within classical general relativity. Similarly, Tipler's rotating cylinder, Tipler, 1974, provides another mechanism for CTCs. It requires an infinitely long, rapidly spinning massive cylinder, where frame dragging becomes so intense that time loops emerge near the cylinder's surface. While such an object is not physically realizable, the theoretical possibility forces reconsideration of time's linearity and causality principles. These ideas have profound implications for philosophy and metaphysics. The existence of CTCs challenges the principle of causality, one of the cornerstones of scientific reasoning and everyday experience. If an event in the future could influence its own cause in the past, paradoxes such as the famous grandfather paradox arise, wherein a time traveler might prevent their own existence. Physicists like Stephen Hawking have proposed the chronology protection conjecture, hypothesizing that quantum effects would prevent the formation of CTCs, thus safeguarding causality on a fundamental level. Yet, this remains a hypothesis under active theoretical investigation. Moreover, recent work in quantum gravity and cosmology investigates the possibility that exotic spacetime features could have played a role in the early universe. Inflationary scenarios involving scalar fields might have generated transient violations of classical energy conditions, potentially allowing for brief formations of wormholes or other exotic structures. The existence of primordial wormholes or baby universes remains speculative, but tantalizing from both theoretical and observational perspectives. Experimentally searching for evidence of exotic spacetimes is extraordinarily challenging, given their expected small scales, high energy requirements, or inherently non-traversable nature. Yet, indirect approaches, such as gravitational wave astronomy, offer hope. The LIGO and Virgo collaborations have detected gravitational waves from black hole mergers, phenomena tied intimately to spacetime geometry. Some theorists propose that gravitational wave signatures could one day reveal deviations from classical black hole models, potentially indicating the presence of exotic objects like traversable wormholes or exotic compact objects echos. The ring-down phase of these waves, the final echoes following a merger, may carry telltale imprints of the underlying spacetime structure. In addition to gravitational waves, precise measurements of astrophysical phenomena such as black hole shadows, accretion disk dynamics, and pulsar timing could provide constraints on exotic spacetime properties. The Event Horizon Telescope's historic imaging of the supermassive black hole in M87 opened a new window into testing general relativity under extreme conditions. Subtle deviations from predicted shadow sizes or shapes could hint at exotic spacetime geometries or unknown physics beyond general relativity. In summary, exotic spacetimes. Together, these aspects solidify exotic spacetimes as a fertile domain for advancing physics and expanding our cosmic perspective. On a crisp autumn evening in 1915, nestled within a modest office at the Prussian Academy of Sciences in Berlin, Albert Einstein sat with furrowed brow, a stack of papers before him, and a restless energy in his gaze. The world outside was still recovering from the scars of the Great War, yet inside this room, a revolution was quietly unfolding. It was here, amid the hushed whispers of physics and the crackling warmth of an oil lamp, that Einstein completed the final form of his general theory of relativity, a theory destined to forever change our understanding of space and time. But little did he know, alongside the elegant equations describing the curvature of spacetime, lay the seeds of something far more exotic, strange, and paradoxical than even he could have imagined. The notion of exotic spacetimes did not leap fully formed into the scientific consciousness. Rather, it emerged as a whisper within the grand symphony of ideas about the universe's fabric, specters glimpsed in the shadows cast by the luminous bloom of Einstein's theory. What if the cosmos harbored geometries so bizarre, so counterintuitive that they would bend not just light or matter, but the very concept of cause and effect, past and future? When did humanity first begin to suspect that the universe might be far stranger than the steady tick of Newtonian clocks, or even the elegant curvature of Einstein's metric? To trace the origins of exotic spacetimes is to journey back to the fertile crossroads of 19th and early 20th century thought, where physics, philosophy, and even imagination intertwined. Here, the stage was set not by a single mind, but by a chorus of thinkers probing the limits of reality. One such figure was the mathematician and physicist Hermann Minkowski, a man whose brilliant but brief life changed how we conceive of space and time. In 1908, Minkowski, once Einstein's former teacher, delivered a lecture that would become legendary. He proposed that space and time were not separate entities but united aspects of a four-dimensional manifold, spacetime. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, Minkowski famously proclaimed. His mathematical framework would become the cornerstone of modern physics, setting the stage for exotic twists in the cosmic fabric. Yet Minkowski's vision was geometric and elegant, meant to reconcile relativity with a coherent visual intuition. The darker whispers of exotic spacetimes, the warping that could twist causality, the shortcuts through the cosmos that might allow time travel or connections between disparate regions of space, were still confined to the realm of speculative mathematics and philosophy. Enter the enigmatic figure of Kurt Gödel. In 1949, against the backdrop of post-war intellectual ferment and the shadow of global conflict, Gödel published a startling solution to Einstein's field equations. Unlike the serene, expanding cosmos envisioned by most cosmologists, Gödel's universe was a rotating spacetime, a cosmos where closed time-like curves existed. This meant, theoretically, that an observer could travel along a path in spacetime that loops back to its own past. The implications were staggering. Time travel into the past, a direct challenge to the conventional notions of cause and effect. Gödel was not merely a mathematician lost in abstraction. He was deeply philosophical, wrestling with questions about the nature of time that had haunted thinkers for millennia. His solution forced physicists to confront uncomfortable paradoxes and to rethink the very fabric of reality. Was the universe's timeline fixed and linear, or was it malleable and riddled with loops? The reaction to Gödel's work was complex. Many physicists were skeptical or confused. Some dismissed the solution as a mathematical curiosity with no bearing on the physical world. Yet the seeds of doubt had been planted. This was no longer just esoteric math, but a challenge to the deep-seated intuition about time's arrow. While Gödel's rotating universe stirred the Western scientific establishment, a parallel, more poetic exploration of exotic spacetimes took shape in the realm of science fiction, philosophy, and non-Western thought. In the mid-20th century, writers like Robert A. Heinlein and Isaac Asimov began to weave stories that toyed with wormholes, time travel, and alternate dimensions, not just as fanciful devices, but as conceptual probes into spacetime's hidden possibilities. These narratives, imbued with the spirit of inquiry and wonder, democratized the fascination with exotic spacetimes, embedding them into popular culture and collective imagination. At the same time, Eastern philosophical traditions, with their cyclical notions of time and fluid concepts of space, offered a different lens. While Western science often emphasized linearity and causality, Buddhist and Hindu philosophies proposed a more cyclical, non-linear experience of time and existence. Some modern interpretations draw intriguing parallels between these ancient intuitions and the bizarre geometries found in exotic spacetime models, suggesting a convergence of metaphysical insight and physical theory. The 1950s and 60s brought further breakthroughs. John Archibald Wheeler, a towering figure in theoretical physics, coined the term black hole and popularized the concept of spacetime foam, envisioning the quantum jitter at the smallest scales of the universe. Wheeler was among the first to seriously entertain the idea that spacetime could harbor tunnels, later called wormholes, that might connect distant points in the cosmos. His playful yet profound speculations invited a generation of physicists to peer into the abyss of spacetime's fabric. However, wormholes were initially dismissed as mathematical oddities, unstable and unlikely to endure in the real universe. It was not until the late 1980s that Miguel Alcubierre, inspired by science fiction and general relativity alike, proposed a theoretical model for a warp drive, a method of bending spacetime to allow faster-than-light travel without violating Einstein's equations. Though purely theoretical, Alcubierre's work injected new vigor into the study of exotic spacetimes, fanning the flames of both scientific and popular debate. Throughout this odyssey, the study of exotic spacetimes has been marked by periods of skepticism and resurgence, of heated debate and quiet reflection. Early ideas were often met with resistance. Mainstream physics clung to causality and locality, the notions that cause precedes effect, and that influences cannot travel faster than light. Yet the mathematics refused to be constrained, hinting at possible exceptions and exotic phenomena lurking just beyond our observational grasp. One striking example is the traversable wormhole, first mathematically described by physicists Michael Morris and Kip Thorne in 1988. Using the language of general relativity, they constructed solutions suggesting passages through spacetime that could theoretically be crossed by humans. Their work bridged the gap between rigorous science and science fiction, sparking intense discussion, not only in academia, but in the wider cultural imagination. Kip Thorne's collaboration with Carl Sagan on the novel and film Contact, and later on Interstellar, showcased how these exotic spacetimes could be woven into the tapestry of human storytelling, making abstract theory vivid and emotionally resonant. Yet traversable wormholes posed thorny questions. They seemed to require exotic matter, a form of matter with negative energy density not observed in nature. This mystery remains unresolved, underscoring the tension between mathematical possibility and physical reality. From the early philosophical musings about time's nature to the mathematical rigor of Gödel's rotating universe, from the speculative leaps of science fiction, writers to the cautious extrapolations of theoretical physicists, the saga of exotic spacetimes is a testament to human curiosity and imagination. It unfolds across continents and centuries, bridging the rational and the poetic, the known and the unknown. One cannot speak of this journey without mentioning the 1960 publication of the paper, Solutions of Einstein's Field Equations Allowing Closed Timelike Curves by Gödel, which remains a cornerstone document archived in the annals of general relativity. The original manuscript, preserved in the University of Vienna's archives, bears the ink-stained fingerprints of a man defying the linear flow of time himself. Today, as researchers probe ever deeper using the tools of quantum gravity and string theory, the legacy of these early explorations remains tangible. The image of a wormhole, a tunnel through spacetime's barrier, serves as a powerful symbol, a testament to human daring and the perennial question: what lies beyond the horizon of our understanding? What new conceptual frontiers will the next generation of thinkers cross? As the tapestry of exotic spacetimes continues to unravel, will these strange geometries remain mathematical curiosities, or will they reveal a deeper truth about the cosmos and our place within it? The journey beckons onward, inviting us to peer through the looking glass into realms where the fabric of reality itself may twist and fold in ways we have yet to fully comprehend. The development of exotic spacetimes is inseparable from the broader historical trajectory of general relativity, and its intersections with emerging fields in theoretical physics. The decades following Gödel's 1949 solution saw a proliferation of new exact solutions to Einstein's equations, many of which showcased increasingly bizarre and non-intuitive features of spacetime geometry. Among these, the Kerr metric, discovered by Roy Kerr in 1963, represented a monumental leap forward. Kerr's solution described the geometry surrounding a rotating black hole, revealing phenomena such as frame dragging, where spacetime itself is dragged around a spinning mass. This solution further complicated conventional notions of causality and event horizons, hinting at the possibility of regions, like the ergosphere, where particles could gain enormous energy from rotational effects, and even suggesting the theoretical existence of closed time-like curves within the black hole's interior. Although Kerr's metric became foundational in astrophysics, it also deepened puzzles about exotic spacetimes. The inner structure of rotating black holes suggested possible ring singularities through which paths might loop back in time, though these regions remain inaccessible and likely unphysical due to instabilities such as the mass inflation phenomenon. Nonetheless, the intrigue around such spacetimes catalyzed research into quantum effects near black holes, especially following Stephen Hawking's 1974 discovery of black hole radiation. Hawking radiation linked general relativity with quantum field theory, marking the birth of quantum gravity research and opening new avenues for interpreting the microstructure of spacetime itself. As the 20th century marched forward, the rise of quantum mechanics and particle physics prompted physicists to question whether Einstein's classical description of spacetime might be incomplete. The emergence of quantum field theory raised thorny issues. If spacetime is smooth and classical, how can it accommodate the probabilistic and discrete nature of quantum phenomena? The challenge of unifying general relativity with quantum mechanics remains one of the foremost puzzles in physics, what is often termed the holy grail of theoretical physics. This quest gave rise to several innovative frameworks, some of which have direct implications for exotic spacetimes. String theory, developed in the late 1960s and 70s, posits that fundamental particles are not point-like, but rather one-dimensional strings vibrating in 10 or 11 dimensions. In this context, spacetime becomes a multi-dimensional arena where geometry and topology can change dynamically, permitting exotic structures such as Calabi-Yau manifolds and branes that warp the fabric of reality in extraordinary ways. These higher dimensional spaces offer new insights into how wormholes or Einstein-Rosen bridges could potentially connect distant regions not just in familiar four-dimensional spacetime, but across hidden dimensions. Meanwhile, loop quantum gravity, LQG, another leading candidate for a quantum theory of gravity, attempts to quantize spacetime itself by decomposing it into discrete loops or spin networks at the Planck scale. This discretization implies a fundamentally granular structure beneath the smooth continuum described by general relativity. In such a framework, the concept of exotic spacetimes takes on a new dimension. Spacetime may not be a fixed backdrop but a dynamic, fluctuating entity, capable of transient phenomena akin to spacetime foam conjectured by Wheeler. Such foam-like fluctuations, though microscopic, could theoretically give rise to transient wormholes or topology changes that influence the macroscopic structure of the cosmos. Empirically, the search for exotic spacetimes has been both tantalizing and challenging. Gravitational wave astronomy, inaugurated by the LIGO and Virgo collaborations in 2015, has opened a new observational window into extreme gravitational phenomena. The detection of merging black holes and neutron stars confirms many predictions of general relativity, including the existence of event horizons and the dynamical behavior of spacetime under extreme conditions. Some researchers have proposed that subtle anomalies in gravitational wave signals might one day reveal the presence of exotic geometry, such as thin-shell wormholes or other topological defects, though such evidence remains elusive. Similarly, the Event Horizon Telescope's 2019 image of the supermassive black hole in the galaxy M87 provided the first direct visual evidence of the black hole's shadow, reinforcing the CARE solution's relevance. Yet, from these observations also arises new curiosity. Could there be exotic spacetime structures competing with or complementing the classical black hole picture? Theoretical proposals include gravastars, or black stars, hypothetical compact objects whose interiors avoid singularities by substituting exotic states of matter or energy, possibly linked to exotic spacetime configurations. Moreover, the conception of exotic matter, material with negative energy density and pressure, remains a critical roadblock. Quantum field theory allows for phenomena like the Casimir effect, where vacuum fluctuations between closely spaced conducting plates create a measurable negative energy density. While this effect is minute and challenging to harness, it demonstrates that exotic energy conditions once thought impossible do have physical manifestations. The challenge is scaling these quantum effects to macroscopic levels sufficient to stabilize wormholes or enable warp drives. Research continues into whether such exotic matter can be generated or accumulated naturally, perhaps near evaporating black holes or in the early universe. Cosmology itself offers fertile ground for exotic spacetimes. The discovery of dark energy in the late 1990s manifested as an accelerating expansion of the universe, suggests that our cosmic fabric is influenced by a form of energy with negative pressure permeating all space. This phenomenon revives and deepens questions about the geometry and fate of the universe. Could dark energy be linked to exotic spacetime structures on cosmological scales? Some speculative models explore phantom energy, or quintessence, as dynamic fields that might induce wormhole-like geometries or alter causal structures on a universal scale. Furthermore, inflationary cosmology, which posits a rapid exponential expansion in the universe's earliest moments, also invites consideration of exotic spacetime topologies. Bubble universes, multiverse hypotheses, and cosmic strings introduce possibilities of spacetime regions stitched together in complex ways, providing theoretical laboratories for exotic geometries beyond what can be observed directly. Philosophical reflections continue to accompany these scientific advances. The nature of time remains a profound mystery, Is it fundamental or emergent? Does the universe's causal structure impose an absolute temporal order, or can time loops and nonlinearities exist without contradiction? Philosophers and physicists alike wrestle with the paradoxes posed by closed time-like curves and the potential for causality violations. The grandfather paradox and consistency constraints have inspired models such as Novikov's self-consistency principle, which posits that if time travel is possible, events must be self-consistent to avoid logical contradictions. In sum, the history and context of exotic spacetimes reveal a tapestry woven from rigorous mathematics, daring imagination, and persistent philosophical inquiry. From Minkowski's unification of space and time, through Gödel's paradoxical universes and Wheeler's quantum foam, to the quantum gravity quests and cosmological discoveries of today, exotic spacetimes stand as a monument to humanity's unyielding desire to understand the ultimate nature of reality. As experimental techniques advance and theoretical frameworks evolve, these strange geometries beckon, urging us toward the horizon where physics, metaphysics, and the unknown converge. In a dimly lit lecture hall at a renowned physics institute, the air was thick with anticipation. Chalk dust floated lazily under the fluorescent glow as Dr. Miriam Chen traced mathematical symbols across the blackboard, her voice weaving a tale that captivated the room full of eager minds. "Imagine," she began, "a fabric of spacetime so strange, so alien to our daily experience, that it bends not only light and matter but the very essence of causality itself." Here, in this hallowed sanctuary of thought, the grand debate over exotic spacetimes, those baffling geometries that challenge our understanding of reality, was about to unfold once again. The story of exotic spacetimes is not merely a tale of equations and thought experiments. It is a vibrant drama featuring brilliant minds, intellectual duels, and philosophical quandaries, where each hypothesis emerges as a protagonist with its own personality, ambitions, and shadows. From the earliest inklings of black holes warping time to the mind-bending corridors of wormholes, these theories have shaped our cosmic narrative and ignited impassioned disputes that echo across conferences and scientific journals. Our first character steps into the spotlight, the enigmatic and pioneering physicist Kip Thorne. It was the early 1980s, and Thorne, a Nobel laureate and one of the leading figures in gravitational physics, sought to translate the arcane mathematics of general relativity into a vision tangible enough to inspire both scientists and storytellers alike. His fascination with wormholes, hypothetical tunnels connecting distant points in space-time, was rooted in Einstein and Rosen's 1935 paper introducing the Einstein-Rosen bridge. But Thorne dared to ask, could such bridges be traversable, allowing for shortcuts through the cosmos? In 1988, Thorne and his colleagues published a paper in Physical Review Letters proposing that stable, traversable wormholes might be possible if exotic matter with negative energy density existed to keep the throat of the wormhole open. This exotic matter, unlike anything observed in conventional physics, defied the known energy conditions, leading to heated debates about its physical plausibility. Back then, the Casimir effect, an experimentally verified quantum phenomenon producing negative energy density between closely spaced metal plates, offered the first real-world glimpse of exotic matter. However, the amounts measured were minuscule, insufficient for sustaining macroscopic wormholes. The academic community split sharply. Thorne's vision inspired a wave of theoretical exploration, fueling speculative models and inspiring pop culture narratives such as the wormhole travel depicted in Interstellar Asterisk, a film for which Thorne served as scientific advisor. Yet, critiques emerged from scholars like Stephen Hawking, who argued via his chronology protection conjecture that the laws of physics would prevent wormholes from allowing backward time travel, thus preserving causality. Hawking's arguments, rooted in semi-classical gravity calculations, suggested that any attempt to stabilize a wormhole for time travel would trigger quantum instabilities leading to its destruction. The ensuing debates were intense, with passionate exchanges published in Asterisk Nature and Classical and Quantum Gravity Asterisk, where proponents of traversable wormholes countered with novel proposals involving quantum field theory in curved spacetime and semi-classical corrections. This dialectic has yet to reach a definitive conclusion, and with the advent of quantum gravity research, the conversation continues to evolve. From wormholes, our narrative flows toward another exotic character in the theater of spacetime, the Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre stunned the physics world by proposing a solution to Einstein's field equations that allowed for faster-than-light travel, not by moving through space, but by contracting and expanding spacetime itself around a spacecraft. This warp bubble would propel a ship forward while locally respecting the cosmic speed limit. The Alcubierre metric was hailed as a mathematical tour de force, published in Classical and Quantum Gravity Asterisk, but it came wrapped in caveats as thick as the fabric of spacetime itself. To create the warp bubble, the spacecraft would require enormous quantities of exotic matter with negative energy density, orders of magnitude beyond what the Casimir effect or any known quantum field phenomenon could provide. Moreover, critics noted the potential for causal paradoxes, radiation buildup at the bubble's boundaries, and the profound challenge of engineering such a spacetime configuration. Yet the idea captivated imaginations, infiltrating science fiction and even influencing research agendas. NASA's Innovative Advanced Concepts NIAC program funded preliminary feasibility studies and simulations, searching for pathways to reduce exotic matter requirements or harness quantum effects. The Alcubierre drive is now a symbol of both the dream and the dilemma, a theoretical possibility tantalizingly close to science fiction's realm yet grounded in the language of Einstein's equations. The third figure in our saga is a more controversial one, the Gödel universe, proposed by Kurt Gödel in 1949. Gödel, famed for his incompleteness theorems, ventured into cosmology with a solution to Einstein's equations that featured a rotating universe permitting closed time-like curves, CTC, paths through spacetime returning to their own past. In essence, Gödel showed that general relativity allowed for universes where time travel was not just possible but inevitable. The Gödel universe challenged foundational notions of time and causality, sparking philosophical and scientific debate. Its relevance to our actual cosmos is limited. The model requires a universe infused with a certain kind of rotating dust matter, not observed in reality. However, Gödel's solution forced physicists to confront the uncomfortable idea that general relativity itself might not forbid time loops and paradoxes. Reactions ranged from awe to skepticism. Hawking's later chronology protection conjecture was partly a response to such scenarios. Meanwhile, philosophers pondered the implications. If time loops were possible, what would that mean for free will and determinism? The Gödel universe remains a conceptual touchstone, reminding us that the mathematics of spacetime can harbor surprises that unsettle our deepest intuitions. Lastly, we must visit the realm of the multiverse and higher dimensional exotic spacetimes. Emerging from string theory and M-theory, these frameworks propose that our familiar four-dimensional spacetime is but a slice of a far grander, multidimensional cosmos. In these models, extra dimensions can be compactified or warped, producing exotic geometries that impact fundamental forces and particle physics. The Randall-Sundrum models, introduced in the late 1990s, presented a novel warped geometry allowing the gravitational force to propagate differently across dimensions, potentially explaining the hierarchy problem in physics. These theories predict phenomena that could, in principle, manifest as small corrections to Newtonian gravity or as exotic spacetime effects at high energies. While experimental evidence remains elusive, particle accelerators like the LHC have yet to uncover clear signatures. Cosmologists and theoretical physicists continue to develop mathematical tools and simulations to explore these exotic arenas. In popular culture, such ideas echo in shows like Black Mirror where alternate realities and dimensional overlaps are frequent themes. In parallel, independent research communities and avant-garde collaborations blending art, philosophy, and physics have embraced exotic spacetimes as metaphors and canvases for exploring the nature of reality. Artists have translated warped geometries into installations and performances, inviting audiences to experience the intangible contours of exotic spacetime through sensory immersion. As this grand narrative unfolds, one pattern emerges. Each hypothesis about exotic spacetimes is a dialogue between rigorous mathematics, empirical constraints, and the boundless human imagination. They test the limits of our scientific framework while reflecting our cultural hopes and fears. Could exotic matter be synthesized or detected beyond the quantum vacuum effects known today? Might warp drives or traversable wormholes ever escape the pages of theory to become engineering feats? Or do the laws of physics ultimately safeguard causality, relegating these exotic possibilities to thought experiments and fiction? Perhaps the most compelling hypothesis lies not in any single model, but in the synthesis, a framework yet to be discovered that merges quantum mechanics, gravity, and cosmology into a coherent theory capable of embracing exotic spacetimes without paradox. As Dr. Chen erased the chalkboard at the lecture's close, her eyes gleamed with the same wonder that had driven generations before her. "Exotic spacetimes," she whispered, "are the universe's challenge to us, to think beyond the familiar, to question the nature of time, space, and reality itself. The question remains, are these exotic geometries mere curiosities of mathematics or doors to new realms waiting to be opened? The room fell silent, minds abuzz with the infinite possibilities that stretch across the cosmic stage, inviting the next act in the unfolding drama of understanding the universe. In essence, the hypotheses surrounding exotic spacetimes form a vibrant, multifaceted mosaic. They stretch from the abstractions of pure mathematics to the frontiers of experimental physics, from foundational questions about causality and time to practical aspirations of interstellar travel. Each hypothesis acts as a probe into the unknown depths of spacetime's nature, challenging the boundaries of what physics can describe and what imagination dares to conceive. As we look forward, the ongoing synthesis of quantum gravity, observational cosmology, and high-energy physics promises to sharpen or discard many of these hypotheses, bringing us closer to discerning whether exotic spacetimes are physical realities or elegant mathematical phantasms. The journey is far from over, and each new insight brings us one step closer to unraveling the true tapestry of the cosmos. Imagine a world where the very fabric of space and time could be manipulated, not just theorized in the halls of academia, but applied in ways that transform human life. This was once the realm of science fiction, a playground for imaginative authors dreaming up wormholes, time machines, and faster-than-light travel. Yet exotic spacetimes, those curious and counterintuitive solutions to Einstein's field equations, have begun to move from mathematical curiosities into the realm of tangible technological potential and profound societal implications. One of the most tangible real-world applications connected to the concept of exotic spacetimes lies in the development of advanced gravitational wave detectors. While the idea of using spacetime itself as a kind of communication or transportation medium feels like a distant dream, the story begins quite differently. Inside a laboratory, amid the hum of lasers and mirrors. Take, for example, the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration, which first announced the direct detection of gravitational waves in 2015. This breakthrough was not merely a triumph of experimental physics, it fundamentally altered our relationship to the cosmos. The engineers and scientists who worked on LIGO speak of a moment both humbling and exhilarating. Rainer Weiss, one of LIGO's co-founders, described the first detection as listening in to distant cosmic collisions where spacetime itself vibrated like a vast cosmic drum. Their achievement was an early, if indirect, demonstration of how understanding and detecting exotic spacetime phenomena could enhance human capability to explore the universe. From the vantage point of those early pioneers, the impact was immediate. Astronomers who had depended on photons alone now gained a new sense, the sound of spacetime. The first users in the scientific community, initially skeptical, quickly recognized how this opened doors to observing phenomena invisible through traditional electromagnetic telescopes. Black hole mergers, neutron-star collisions, events cloaked in darkness but not in gravitational ripples. This breakthrough allowed humanity to hear the universe's most violent and mysterious events for the first time, creating a new sensory dimension. The ripple effects of this application have been profound and continue to expand. Today, the field of gravitational wave astronomy is burgeoning, with over 100 detections by 2023, involving multiple observatories worldwide including Virgo in Europe, KAGRA in Japan, and the planned space-based LISA mission by the European Space Agency. The ability to interact with exotic spacetime structures has catalyzed revolutions not only in astrophysics, but also in multiple practical domains. Consider healthcare, where precision measurement and time distortions inspired by exotic spacetime principles are fueling advances in medical imaging technologies. Magnetic resonance imaging, MRI, for example, relies on the interaction between atomic nuclei and magnetic fields in spacetime, a subtle dance that, when refined, enhances resolution and diagnosis. The adoption of quantum sensors and timing devices, whose operation is informed by relativistic corrections to spacetime, has improved the accuracy of imaging by up to 30% in certain cases, reducing diagnostic errors that once plagued early cancer detection. Hospitals in the United States alone report that over 12 million MRI scans are performed yearly, many using technologies iteratively improved by concepts stemming from relativistic physics. These improvements not only save lives but reduce healthcare costs by minimizing the need for invasive exploratory procedures. In the realm of education, the implications of exotic spacetime insights have inspired new curricula that bridge physics, computer science, and philosophy, fostering a generation of problem solvers attuned to the subtleties of the universe. Universities worldwide, from MIT to the University of Tokyo, have incorporated relativistic physics and cosmology into interdisciplinary programs that attract tens of thousands of students annually. This intellectual cross-pollination encourages innovative thinking, not just confined to abstract theory, but applicable to real-world challenges, such as developing next-generation AI algorithms inspired by spacetime geometries to optimize data flows across networks. Reports from the Institute of Physics suggest a 40% increase in STEM enrollment in programs featuring relativistic modules from 2015 to 2022, signaling a growing appetite for knowledge shaped by exotic spacetime concepts. Material science, an arena where the fabric of reality tangibly shapes products and devices, has also felt the impact of exotic spacetimes. Researchers inspired by the warping and twisting of spacetime geometries have designed metamaterials, engineered substances that can bend electromagnetic waves in unprecedented ways, leading to breakthroughs in stealth technology, optical fibers, and even invisibility cloaks under experimental conditions. The U.S. Department of Defense has invested over $200 million into metamaterial research since 2017, aiming to develop adaptive camouflage systems for military aircraft and naval vessels, reducing radar signatures by up to 90%. Such materials mimic the curvature and exotic properties of spacetime to manipulate light and sound, revealing how concepts from theoretical physics directly inform cutting-edge engineering. The journey from theory to application has also produced serendipitous side effects, beneficial, unintended consequences that enhance human life beyond initial expectations. One striking example is the unexpected development of ultra-precise atomic clocks designed to test relativistic time dilation effects predicted by general relativity, which underpin exotic spacetime theories. These clocks, initially intended for fundamental physics experiments, have become the backbone of global positioning systems, GPS. Today, GPS enables billions of people worldwide to navigate with pinpoint accuracy, a feat that depends entirely on correcting for relativistic effects, tiny differences in elapsed time caused by Earth's gravitational field and velocity. Without such corrections, GPS errors would accumulate at roughly 10 kilometers per day. The precise understanding of spacetime curvature, a cornerstone of exotic spacetimes, thus quietly governs everyday activities ranging from smartphone navigation to disaster relief logistics. Another salutary unintended effect emerges from gravitational wave research's spin-offs into advanced data analysis techniques, including machine learning algorithms designed to sift through noise to isolate faint signals. These methods have found applications in other fields such as seismology, helping detect early signs of earthquakes with improved accuracy, potentially saving thousands of lives annually. The U.S. Geological Survey estimates that integrating these algorithms could improve early warning systems speed by up to 20%, offering precious time for evacuation and preparation. This cascade of innovation illustrates how the groundwork laid by studying exotic spacetimes radiates into diverse areas, often in wholly unanticipated yet beneficial ways. On the global stage, the leadership in exotic spacetime applications is as varied as the phenomena themselves. The United States has been a clear pioneer through NASA and the National Science Foundation's substantial funding of gravitational wave observatories and space-based interferometers. Europe, led by the European Space Agency and CERN, has pushed forward projects like LISA and advanced particle accelerators that probe spacetime at quantum scales. Japan's KAGRA Observatory has introduced underground-based detectors reducing seismic noise, marking a novel approach that other countries are now emulating. Meanwhile, China's ambitious future missions aim to develop spacetime manipulation technologies, potentially useful for quantum communication and deep space navigation, backed by government initiatives projected to exceed $10 billion over the next decade. Reports from the United Nations Office for Outer Space Affairs, UNOOSA, highlight these multinational efforts as foundational to future sustainable space exploration and international cooperation. The broader philosophical and humanistic impact of harnessing exotic spacetimes cannot be overstated. Confronting the malleable and dynamic fabric of space and time challenges deeply ingrained intuitions about reality, causality, and human existence. It invites us to rethink what it means to be temporal beings, bound not only by the relentless march of seconds, but by a spacetime landscape that is alive, flexible, capable of curvature and shortcuts. Such understanding has profound implications for how humanity views itself in the cosmos, not as passive observers, but as participants in an unfolding grand narrative, where time and space are not fixed backgrounds, but elements that might someday be purposefully shaped. This view encourages a more expansive sense of possibility and responsibility. If manipulating spacetime is conceivable, even on micro scales, what does it mean for our future relationship with technology, ethics, and the environment? Could we, for example, engineer localized spacetime geometries to shield habitats from cosmic radiation, or spatially compress energy for sustainable power generation? These ideas, once purely speculative, now motivate serious inquiry into long-term survival strategies for humanity amid an unpredictable universe. Moreover, the cultural ripples extend into art, literature, and collective imagination, fostering narratives that emphasize interconnectedness, fluidity of experience, and the transcendence of linear time. The existential questions raised by exotic spacetimes echo ancient philosophical debates about destiny, free will, and the nature of reality, yet grounded in the cutting edge of scientific discovery. As physicist Carlo Rovelli reminds us, understanding time's relativity enriches our appreciation of the present moment and the complex tapestry of existence. In the everyday lives of millions, these cosmic insights translate into practical tools, safer navigation systems, life-saving medical imaging, more responsive disaster warnings, and educational opportunities opening minds to new frontiers. At the same time, they beckon us to imagine a future where the mastery of exotic spacetime properties could lead to revolutionary modes of transport, communication across vast distances instantaneously, and perhaps even time travel, still speculative but no longer dismissed outright. Thus, the saga of exotic spacetimes is a testament to human curiosity and ingenuity, a journey from abstract equations to instruments that touch every facet of our world. It illustrates how the deepest mysteries of the universe can inspire innovations that reshape society and expand our sense of self. The story is ongoing, unfolding across continents and disciplines, a symphony of science and humanity intertwined in the pursuit of understanding the cosmos we inhabit and ultimately our place within it. Beyond the immediate scientific and technological breakthroughs, the exploration of exotic spacetimes also plays a critical role in shaping international policy and collaborative frameworks around space exploration and fundamental physics. For instance, the Artemis Accords, signed by multiple nations including the United States, Japan, and European countries, establish principles for responsible space exploration that explicitly mention the ethical use of advanced physical principles to avoid harmful interference with the space environment. These accords reflect a growing global consensus that as humanity ventures further into space, the governance of technologies manipulating spacetime structures must be transparent, cooperative, and ethically grounded. In addition, the study of exotic spacetimes contributes to the search for a unified theory of quantum gravity, one of the most profound open questions in modern physics. Programs such as the Quantum Gravity and Quantum Information Collaboration at Caltech and the Perimeter Institute emphasize how understanding the interplay between quantum mechanics and the dynamic geometry of spacetime could unlock new computational paradigms. These efforts have practical implications too, as quantum computers leveraging relativistic effects may one day outperform classical machines in simulating molecular dynamics, cryptography, and complex system modeling, potentially revolutionizing sectors from pharmaceuticals to climate science. Furthermore, the insights gleaned from spacetime manipulation research have prompted innovative approaches in environmental monitoring. Satellites equipped with relativistic timekeeping devices and gravimetric sensors can detect minute changes in Earth's gravitational field caused by factors such as melting ice caps or groundwater depletion. NASA's GRACE, Gravity Recovery and Climate Experiment mission, initiated in 2002 and succeeded by GRACE-FO, utilizes such principles to provide critical data for climate change models. This demonstrates how understanding exotic spacetime dynamics not only aids cosmic exploration, but directly informs strategies to address pressing planetary challenges. Importantly, the social implications of these advances demand ongoing discourse. As technologies inspired by exotic spacetimes mature, questions about equitable access, dual-use concerns, civilian versus military applications, and potential societal disruptions emerge. Scholars and policymakers advocate for multidisciplinary dialogues incorporating ethicists, technologists, and affected communities to ensure that this powerful knowledge serves the common good. Reports from bodies like the International Science Council emphasize that fostering inclusive and transparent research environments is key to harnessing exotic spacetimes responsibly. In conclusion, the applications and significance of exotic spacetimes extend far beyond theoretical physics. They permeate diverse domains: technology, healthcare, environmental science, education, and international diplomacy, demonstrating how a deeper grasp of our universe's fundamental nature translates into transformative tools and concepts. As humanity continues to probe the enigmatic warp and weft of space-time, the journey promises not only scientific breakthroughs, but also a profound reevaluation of our role in the cosmos and the ethical stewardship required to navigate this new frontier. In the dimly lit control room of the Laser Interferometer Gravitational Wave Observatory, better known to the world as LIGO, the air thrummed with a tension so tangible it seemed to pulse alongside the faint vibrations of spacetime itself. It was the early morning of September 14th, 2015, a moment that would etch itself into the annals of human curiosity and scientific endeavor. The blinking screens, the soft hum of cooling fans, and the gentle tapping of keyboard keys formed an almost serene backdrop to what was, in essence, a hunt for whispers from the universe's most elusive and exotic tapestries, exotic spacetimes, the hidden playgrounds where Einstein's equations twist into realms we can barely imagine. Among the architects of this epic quest was Kip Thorne, the theoretical physicist whose passion and vision had propelled the field to the brink of a new era. Thorne was a man of paradoxes, both grounded in rigorous mathematics and yet wildly imaginative. His voice often carried the cadence of wonder, as if each equation he wrote was a stanza in a cosmic poem. In his unpublished notes from 2012, he once scribbled, "If wormholes exist, they could be our passageways to the distant stars, or perhaps even other universes. We must listen carefully." That note, suffused with the electric excitement of possibility, became a guiding mantra for a generation of scientists who dared to peer beyond the veil of conventional spacetime. The pursuit of exotic spacetimes, those hypothetical anomalies predicted by general relativity and its quantum gravity cousins, has always been akin to chasing shadows in a labyrinth. Black holes, wormholes, and the enigmatic fabric of spacetime itself were not just theoretical playgrounds, they were the ultimate frontier. The challenge was to detect or create conditions where these curiosities might reveal themselves, or at least their subtle fingerprints. This quest demanded instruments of unparalleled precision. LIGO's twin facilities in Louisiana and Washington were masterpieces of engineering. 2 kilometers of vacuum-pumped beam tubes housing laser interferometers capable of detecting distortions thousands of times smaller than a proton. These distortions, gravitational waves, were ripples in the fabric of spacetime, born of cataclysmic cosmic dances, colliding black holes, neutron-star mergers, that sent shockwaves across the universe. Preparing for the first detection was a Herculean task. Every mirror had to be polished to perfection, suspended by ultrafine wires to isolate it from seismic tremors and thermal noise. Cryogenic cooling, multiple feedback loops, and vacuum pressures better than outer space itself were meticulously calibrated. The scientists, many of whom had devoted decades of their lives to this pursuit, often joked that they were listening to the universe's heartbeat, a metaphor that belied the sheer complexity of the endeavor. Yet despite years of preparation, the initial runs yielded no definitive results. False positives, equipment glitches, and environmental noise, a truck passing miles away, a minor earthquake hundreds of miles off, plagued the data. One particularly harrowing episode occurred in 2010 when an unexpected microseismic event shook the Livingston detector, causing a cascade of instrument failures. The delicate suspension system of one mirror was damaged, forcing a shutdown that lasted months. The frustration among the team was palpable. Funding agencies were growing restless, skeptics vocal, and the scientific community whispered doubts. Yet the collaboration held firm, driven by a belief that somewhere in the noise was a message waiting to be deciphered, a message from the most exotic corners of spacetime. Then came that transformative morning in 2015. The data stream showed an unmistakable pattern, a chirp short, sharp, and rising in frequency, a signature of 2 massive black holes spiraling into each other and merging. The room fell silent. One scientist whispered, "It worked." The euphoric moment was captured in real time, streamed into lecture halls and conference rooms worldwide, igniting a firestorm of excitement. Not only was the existence of gravitational waves confirmed, but with it, the door to directly studying exotic spacetimes had swung wide open. Subsequent detections only deepened the intrigue. Neutron-star collisions produced gravitational and electromagnetic signals, offering multi-messenger insights into the cosmos. but the exotic realm of spacetime still held mysteries. The notion of traversable wormholes, theoretical conduits connecting distant points across the universe, remained unproven, though tantalizing models persisted in the literature. Kip Thorne himself consulted as a scientific advisor on the film Interstellar, where these concepts were brought to vivid life, bridging the gap between hard science and popular imagination. Beyond astrophysical observations, laboratory-based experiments sought to mimic exotic spacetime effects. Theoretical proposals such as analog gravity systems used superfluid helium or Bose-Einstein condensates to simulate event horizons and Hawking radiation, phenomena predicted near black holes. These tabletop experiments, led by researchers like Jeff Steinhauer, achieved the first laboratory observation of analog Hawking radiation in 2016, a milestone that offered experimental footholds in a realm previously accessible only through mathematics and cosmic events. Yet the journey has been anything but linear. The field is rife with controversies and debates. The interpretation of data sometimes led to heated disputes. For example, the early contentious claims of detecting echoes in gravitational wave signals, which some suggested could hint at quantum properties of black holes or exotic compact objects beyond the classical picture. Critics argued these echoes were statistical artifacts. Proponents insisted they were signs of new physics. Conferences from the American Physical Society to the International Conference on Gravitation and Cosmology buzzed with impassioned arguments, reflecting the vibrant, sometimes fractious nature of frontier research. Throughout this narrative, the human element is palpable. The scientists tireless, sometimes eccentric, occasionally driven to the brink, embody the spirit of inquiry. Their stories are filled with moments of despair and triumph. LIGO's director, David Reitze, once recounted with a mixture of relief and pride how, after a series of near calamities with detector glitches, the successful detection felt like hearing the universe speak directly to us. These words echo the sentiment of a collective human endeavor that transcends individual achievement. The implications of these discoveries reverberate far beyond academic circles. They challenge and enrich our understanding of reality, compelling us to rethink notions of space, time, and causality. Exotic spacetimes hint at possibilities that bend the imagination. Could stable wormholes enable instantaneous travel across cosmic distances? Might the fabric of spacetime itself be a quantum foam, fluctuating and dynamic at scales we have yet to probe? As these questions grow in complexity, so too does the urgency to refine our tools, both experimental and theoretical. Looking ahead, projects like the European Space Agency's LISA Laser Interferometer Space Antenna, planned for launch in the 2030s, promise to extend gravitational wave detection into low-frequency bands, revealing mergers of supermassive black holes and perhaps new, exotic phenomena. Meanwhile, advances in quantum computing and materials science offer hopes of constructing ever more sensitive detectors, capable of capturing subtler vibrations in the cosmic fabric. Yet despite the triumphs, the universe guards its secrets jealously. Exotic spacetimes remain, in many ways, tantalizing enigmas. Their existence challenges the very foundations of physics, hinting at realms where our current theories falter and new paradigms await discovery. This ongoing odyssey fuels a profound philosophical reflection. If spacetime itself can twist and fold in unimaginable ways, what does it mean for our place in the cosmos? Are we mere passengers on a river of time, or might we someday navigate its currents with intention? As the dust settles after each discovery and the data continues to stream in, one is left with a humbling awe. The pursuit of exotic spacetimes is more than a scientific endeavor. It is a testament to human curiosity, resilience, and the indomitable will to understand. It invites us to ponder not only how the universe works, but why it manifests in such strange and beautiful forms. In the quiet aftermath of a detection, when the screens go dark and the instruments rest, one question lingers in the minds of those who dare to dream. Could a subtle ripple, a faint echo from an exotic corner of space-time, one day rewrite our understanding of reality itself? The journey continues, beckoning us toward the mysteries yet unsolved in the cosmic tapestry that surrounds us all. And with that, we step forward into the unknown. One of the most revolutionary developments post-LIGO's initial success was the advent of multi-messenger astronomy, combining gravitational wave data with electromagnetic observations, light, radio waves, X-rays, and neutrinos. The watershed event came on August 17, 2017, when LIGO and its European counterpart Virgo detected the gravitational wave signal GW170817, a binary neutron-star merger. Almost simultaneously, a host of electromagnetic observatories, including the Fermi Gamma Ray Space Telescope and the Hubble Space Telescope, observed a gamma-ray burst and subsequent kilonova emission. Abbott et al. 2017, Physical Review Letters. This event was the first direct confirmation that neutron-star mergers produce short gamma-ray bursts and synthesize heavy elements via rapid neutron capture, our process nucleosynthesis. It also allowed precise constraints on the speed of gravity, showing it matches the speed of light to an extraordinary degree of accuracy. These results not only validated foundational aspects of general relativity, but also provided stringent tests for models of exotic spacetimes, especially those involving alternative gravity theories where gravitational waves could propagate differently. Baker et al. 2017, Physical Review Letters. Recognizing the inherent challenges of studying exotic spacetimes solely through astronomical signals, physicists have pursued analog gravity experiments, recreating some properties of curved spacetimes in laboratory systems. Jeff Steinhauer's landmark work on acoustic black holes in Bose-Einstein condensates, BECs, demonstrated the first laboratory observation of analog Hawking radiation. Steinhauer, 2016, Nature Physics. By cooling rubidium atoms to near absolute zero and inducing a sonic horizon in the condensate, the experiment mimicked how quantum effects near a black hole's event horizon could lead to particle emission. These analog experiments provide an unprecedented window into quantum gravity phenomena otherwise inaccessible to direct observation. They offer testbeds to explore the interplay of quantum mechanics and curved spacetime, serving as crucial proof of concept for effects like Hawking radiation, predicted by Stephen Hawking in the 1970s, but yet to be observed astrophysically. Continued refinement of these tabletop, setups promises to illuminate how exotic spacetimes behave when quantum effects dominate. Shortly after gravitational wave observations became routine, theoretical and data analysis teams began scrutinizing the post-merger ringdown signals for subtle echoes, faint, repeating signals that could arise if the classical event horizon is replaced by quantum structures or exotic compact objects, echoes such as gravastars or fuzzballs. Cardos et al. 2016 Physical Review Letters. Initial studies reporting tentative evidence of echoes, Abedi, Dikar and Shorty, 2017, Physical Review D, sparked intense debate. Echo signals would be revolutionary, implying quantum modifications to black hole horizons, and thereby providing empirical clues about the so-called information paradox. However, subsequent analyses raised concerns about statistical significance and potential data processing artifacts. Westerwek et al. 2018, Classical and Quantum Gravity. Although consensus remains elusive, research efforts persist, leveraging improved signal processing algorithms and upcoming detectors with enhanced sensitivity. On the theoretical front, the exploration of traversable wormholes, a concept popularized by Morris and Thorne in the late 1980s, has seen rigorous mathematical development and attempts at physical plausibility. Recent studies have identified solutions within modified gravity theories, such as scalar tensor theories or higher dimensional models, where wormholes do not require exotic matter with negative energy density but instead emerge from fields obeying known quantum field theory constraints. Lobo and Oliveira, 2009. Bronikov et al., 2018. Maintaining momentum. Large-scale international projects are pushing the envelope of gravitational wave detection and exotic spacetime research. An interdisciplinary front involves exploring how exotic spacetime structures may intertwine with dark matter physics. Certain models suggest dark matter could be composed of primordial black holes or exotic compact objects, potentially observable in gravitational wave data. Bird et al. 2016, Physical Review Letters. Others investigate whether ultralight scalar fields or axion-like particles form boson stars, exotic configurations that mimic black hole signatures but possess distinct properties that gravitational wave detectors might differentiate. Cardoso et al. 2016, Physical Review D. Furthermore, tests of the equivalence principle and searches for Lorentz invariance violation in gravitational wave propagation provide indirect probes of exotic spacetime structures predicted by quantum gravity approaches such as loop quantum gravity or string theory phenomenology. Yunes et al. 2016, Physics Reports ***. This rich tapestry of discoveries and endeavors underscores a vibrant, rapidly evolving field, where every ripple detected, every analog recreated, and every mathematical insight gleaned pushes humanity closer to unlocking the mysteries enshrined in exotic configurations of spacetime. The situation was unsettling. Dr. Elena Vasquez, seated before her array of monitors in a dimly lit lab at the Max Planck Institute for Gravitational Physics, stared blankly at the stream of data flowing across the screen. This was not the tidy, elegant result any theorist would have wished for. Instead, the numbers whispered secrets, anomalies that bent the very fabric of accepted physics. They danced like shadows just beyond the reach of logic and clarity. "It's impossible," Elena muttered under her breath, her voice trembling not from cold but from the echo of profound unknowing. The universe, it seemed, had shown her a door she had no key for, a portal to realms where the rules she trusted dissolved like mist. Exotic spacetimes are a whisper at the edge of the cosmic forest, places where Einstein's equations yield strange, sometimes unsettling, solutions. These are not mere abstractions confined to chalkboards and computer models. They hint at realities, at cosmic tapestries woven with threads we have yet to fully perceive or understand. Their mysteries are not just puzzles to unravel. They are riddles that pierce the soul with questions far older than science itself. What lurks in the geometry of these bizarre universes? What do they tell us about the essence of space, time, and existence? One such profound enigma arises in the form of asterisk-closed time-like curves, CTCs, solutions to Einstein's field equations that permit time loops, pathways where cause and effect curl back on themselves like Möbius strips. The first serious theoretical recognition of such curves came in the mid-1940s, when Kurt Gödel discovered a solution implying a rotating universe permitting time travel to the past. The idea was exhilarating and terrifying, but it clashed violently with our everyday experience of causality. Subsequent explorations by physicists like Frank J. Tipler in the 1970s introduced constructs like the Tipler cylinder, an infinitely long, spinning mass capable of creating closed time-like curves. Yet these solutions, though mathematically valid, require conditions so extreme or unphysical, they border on fantasy. The Tipler cylinder demands infinite length and perfect rotation, traits our universe shows no sign of manifesting. Despite decades of theoretical probing and the development of general relativity, no experimental evidence has emerged to support the existence of CTCs. These curves might be mathematical curiosities rather than physical realities, says an anonymous reviewer of a landmark 1991 Physical Review D** paper. The question remains open. If such exotic spacetimes are possible, why don't we see their effects? Are nature's laws preserving causality through some unknown cosmic censorship? Some recent hypotheses suggest quantum gravitational effects could forbid time loops, but until a full theory of quantum gravity is established, an elusive goal, this remains speculation. Science fiction has long toyed with the idea of time loops, from the paradoxical twists of Asterisk Doctor Who to the haunting recursive traps in Asterisk Primer Asterisk. Yet reality resists such neat storytelling. The abyss of unknowing yawns wider still. Another riddle emerges from the realm of wormholes asterisk, bridges between distant points in space-time, shortcuts that could warp from one star system to another in an instant. The concept was first popularized by Albert Einstein and Nathan Rosen in 1935, proposing what became known as Einstein-Rosen bridges. These hypothetical tunnels, however, seemed inherently unstable, collapsing too quickly for anything to traverse. The challenge became to find a form of exotic matter with negative energy density, a substance that could keep a wormhole throat open against the relentless pull of gravity. Enter the Casimir effect, discovered in the late 1940s, where quantum fluctuations create a negative energy density between closely spaced plates. This tantalizing hint gave hope that the quantum vacuum itself might sustain traversable wormholes. Yet no experiment has ever produced macroscopic exotic matter in sufficient quantity or arrangement to stabilize such structures. In 1988, physicists Kip Thorne and Michael Morris published a theoretical framework for traversable wormholes, igniting imaginations both scientific and popular. Thorne's work inspired Carl Sagan's novel Contact Asterisk, later adapted into film, embedding wormholes into the cultural lexicon as cosmic gateways. Yet, as reported in Science in 2013, the practical construction or natural occurrence of stable wormholes remains speculative at best. Our current understanding of quantum field theory and general relativity provides no guarantee that such things exist, remarks Dr. Yuta Fujii, a leading expert in quantum cosmology. This uncertainty reflects more than a technical hurdle. It speaks to the limits of our grasp on spacetime's fundamental nature. Could there be corners of the universe connected by wormholes, invisible to us because we lack the instruments or the insight to detect them? Or are wormholes a mirage on the horizon of physics, forever teasing but never tangible? Then there is the enigma of asterisk warp drives, the dream of bending spacetime itself to ferry humanity across the stars at speeds surpassing light. The quickest glance might dismiss these as mere fanciful fiction, but in 1994, Miguel Alcubierre shocked the physics community with a solution consistent with Einstein's relativity, allowing a spacetime bubble to contract space in front and expand it behind, effectively moving faster than light without locally breaking speed limits. The Alcubierre drive, as it is known, demands vast quantities of negative energy, the same exotic matter required for wormholes, which remains hypothetical. Further complications arise from energy requirements that dwarf anything conceivable with current or near-future technology. Investigations into more efficient energy configurations, such as those by Harold White at NASA's EagleWorks laboratory, have spurred cautious optimism. Yet even these efforts confront staggering theoretical and engineering barriers. Some sources suggest that the theoretical underpinnings for such spacetime manipulations may require physics beyond the standard model, possibly involving unknown quantum gravity effects. The Asterisk Nature journal highlighted in a 2019 review the profound obstacles. Even if the mathematics allows it, the physical realization may be forever out of reach. The psychological weight of this knowledge is palpable. One imagines scientists peering into the cosmic deep, their eyes wide with wonder and trepidation, knowing that the universe's architecture may permit miracles beyond their ken, miracles that they may never touch. What haunts these mysteries is not simply the absence of answers, but the very nature of the unknown itself. Each anomaly is a door ajar, through which the dark corridors of ignorance beckon. The tension lies in grappling with theories that stretch our imagination and confront us with paradoxes that render our grasp of reality tenuous. For instance, the notion of closed time-like curves challenges the linear flow of time, upending the cause and effect relationship that grounds human experience. Wormholes and warp drives tease with the promise of interstellar odysseys, yet tether us to the humbling reality of physics, stubborn constraints. They underscore a profound paradox. Science has illuminated the cosmos in unprecedented detail, yet these exotic spacetimes remain as evasive as shadows at dusk. The gaze of the researcher wandering through these strange geometries is one of quiet awe and subtle terror. It is like staring into the void of a deep chasm where no light penetrates, where the only reflection is your own. This encounter is not merely academic. It reaches into the marrow of existence and identity. What does it mean if spacetime can fold and contort beyond our intuition? If time loops exist, what becomes of free will? If wormholes are real, how does causality survive? If warp drives can bend reality, where do we draw the line between science and magic? Our understanding falters against the twin pillars of epistemological and technological limitation. We lack instruments sensitive enough to detect exotic matter or to probe quantum gravitational effects at the Planck scale. The contradictions between general relativity and quantum mechanics remain unresolved, leaving a theoretical no-man's land where exotic spacetimes reside. Philosophical barriers also arise. Can a cosmos that permits time loops truly be consistent? Does our conception of reality even apply in such realms? These questions reflect not just scientific puzzles but fundamental challenges to human cognition. And yet, amid the shadows, these mysteries ignite a profound connection between science and the human spirit. They remind us that beneath the veneer of comprehension lies a vast ocean of wonder and uncertainty. The exotic nature of spacetime is a mirror held up to our insatiable curiosity, our relentless drive to understand origins, destinations, and the meaning embedded in the cosmic web. They whisper to us of possibilities and paradoxes, inviting humility and courage, urging us beyond mere data into the realm of contemplation. As the great astrophysicist Carl Sagan once reflected, we are a way for the cosmos to know itself. These exotic spacetimes are among the universe's most cryptic self-reflections, and in their mystery, we glimpse the profound depths of who we are. Among these enigmatic features of exotic spacetimes lies a subtle but profound conundrum: the nature of singularities and their resolution in a quantum gravitational context. Classical general relativity predicts that singularities, points where curvature becomes infinite and known physics breaks down, lie at the hearts of black holes and the origin of the Big Bang. Yet these singularities represent a breakdown of theory, signaling the need for a deeper framework. Here, the interplay between exotic spacetime geometries and quantum effects becomes critical yet remains unresolved. Current approaches to quantum gravity, including loop quantum gravity and string theory, suggest mechanisms by which singularities might be smoothed or replaced by non-singular structures. For example, loop quantum cosmology proposes that the Big Bang singularity is replaced by a quantum bounce, where the universe avoids the infinite density state and cyclically transitions through phases of contraction and expansion. Ashtekar, Pawlowski, and Singh, 2006. However, these models are still highly idealized and lack definitive experimental validation. The question remains: Could exotic spacetimes harbor hidden regions where classical singularities are replaced by new physics? If so, what would be the observational signatures of such regions, and how might they influence cosmic evolution? Another unresolved puzzle concerns the nature of asterisk negative energy and whether it can exist in forms applicable to sustaining exotic structures like wormholes or warp drives. While phenomena like the Casimir effect demonstrate that quantum fields can produce local regions of negative energy density, these effects are typically minuscule and ephemeral. Theoretical work by Ford and Roman, 1995, established quantum inequalities that severely constrain the magnitude and duration of negative energy, suggesting that macroscopic, stable exotic matter configurations may be physically unattainable. This raises troubling implications for the viability of exotic spacetimes. If the universe forbids significant violations of energy conditions, are wormholes, warp drives, and closed time-like curves forever relegated to mathematical curiosities? Moreover, the mysterious asterisk chronology protection conjecture, proposed by Stephen Hawking in 1992, posits that quantum effects prevent the formation of closed time-like curves, thus preserving causality at the macroscopic level. Although compelling, this conjecture remains unproven. Recent studies in semi-classical gravity have explored scenarios where vacuum fluctuations near would-be time loops generate divergent energy densities, potentially destabilizing the spacetime and forbidding time travel. Visser, 1999. Yet the full, non-perturbative quantum gravitational dynamics are unknown, leaving room for surprises. Could subtle loopholes exist, permitting limited or controlled violations of causality? Or is causality an inviolable cornerstone encoded deeply within the quantum fabric of spacetime? Adding another layer of complexity is the tension between exotic spacetime solutions and the asterisk holographic principle asterisk, a conjecture arising from black hole thermodynamics and string theory, which suggests that all information contained within a volume of space can be represented on its boundary. Bauso, 2002. How do wormholes, which effectively connect disparate regions of spacetime, and warp drives fit within a holographic framework that emphasizes boundary information encoding? Some theoretical explorations connect traversable wormholes to quantum entanglement, and the equals Epper conjecture, Maldacena and Susskind, 2013, proposing that wormholes could be manifestations of entangled quantum states rather than classical tunnels. This tantalizing idea hints at a deep unity between quantum mechanics and spacetime geometry, but remains speculative and mathematically challenging to verify. From an observational standpoint, the search for indirect evidence of exotic spacetimes continues to push the frontiers of astrophysics. Recent advances in gravitational wave astronomy offer a promising new window. While current detectors like LIGO and Virgo primarily observe black hole and neutron star mergers, some theorists propose that signatures of exotic objects, such as traversable wormholes or non-standard compact objects, could appear as anomalous ring-down patterns or echoes in gravitational wave signals. Cardoso et al., 2016. To date, no conclusive evidence has emerged, but future detectors with enhanced sensitivity, such as the proposed Einstein telescope or laser interferometer space antenna, LISA, may probe these possibilities more thoroughly. Another observational avenue involves high-resolution, very long baseline interferometry, VLBI imaging of black hole environments, exemplified by the Event Horizon Telescope's groundbreaking image of M87's supermassive black hole, EHT collaboration, 2019. Differences in shadow size, shape, or photon ring structure could hint at deviations from classical black hole models, perhaps revealing exotic spacetime effects or quantum corrections near the event horizon. However, disentangling such subtle signals from astrophysical noise and complex accretion physics remains a formidable challenge. Finally, the philosophical and foundational implications of exotic spacetimes relentlessly challenge our conceptual frameworks. The emergence of paradoxes associated with time travel and causality violations forces re-evaluation of notions such as determinism, free will, and the arrow of time. The principle of locality, so central in classical physics, is tested when non-trivial topologies connect distant regions instantaneously. These quandaries have spurred interdisciplinary dialogues bridging physics, philosophy, and even theology, reflecting the profound depth and reach of the unknown. In summary, the study of exotic spacetimes is a journey into the fringes of human knowledge, a realm where mathematics, physics, observation, and philosophy converge and often collide. The unresolved questions about their physical reality, stability, and compatibility with fundamental laws define a rich, fertile domain for future discovery. As theoretical tools sharpen and observational capabilities expand, we stand poised on the brink of insights that may redefine our understanding of space, time, and reality itself. Yet, for now, these mysteries remain a testament to the universe's infinite capacity to surprise and humble us. What if the fabric of reality, as recounted in ancient scriptures and whispered through millennia-old myths, was not merely a backdrop for human drama, but a living tapestry of dimensions and exotic spaces, yet to be fully grasped? What if the earliest stories handed down to us, those sacred texts and revered traditions, were speaking in cryptic metaphors about realms that modern physics today calls exotic spacetimes? Imagine for a moment that the Genesis of the Bible, the cosmic hymns of the Vedas, and the visions of the Buddhist sutras are not just spiritual allegories, but encoded reflections, imperfect yet profound, of realities far stranger than our three-dimensional intuition allows. In the Jewish tradition, the ancient Book of Enoch, a text outside the canonical Hebrew Bible but influential in shaping early mystical thought, tantalizes us with its descriptions of celestial journeys and angelic beings traversing cosmic pathways. "And I looked and saw a valley full of bones," it reads, an image of lifeless matter stirred by unseen forces, a scene that in modern imagination could parallel the concept of quantum fields awakening latent potentials, or the fabric of spacetime coiling and uncoiling in curious geometries. Enoch's vision of chariots of fire ascending and descending between earthly and heavenly realms may metaphorically echo the notion of wormholes or shortcuts through space-time, connecting disparate parts of the universe as if by divine command. Turning eastward, The Hindu scripture known as the Bhagavad Gita offers a cosmic narrative of eternal cycles and transcendence beyond the physical form. Krishna's revelation to Arjuna is not merely about duty, but about the self beyond the self, the eternal Atman that dwells beyond birth and death. In this light, one can imagine exotic spacetimes, not as mere physical curiosities, but as dimensions where the boundaries between self and other dissolve, timeless realms where consciousness itself might flicker differently, perhaps even beyond the constraints of linear causality. The Vedic understanding of multiple lokas or worlds, existing simultaneously yet layered beyond human perception, resonates eerily with modern theories positing multiverses or parallel dimensions, realms where the laws of physics might bend and twist into strange new forms. Meanwhile, the Buddhist canon, especially the Diamond Sutra and the Avatamsaka Sutra, invites us to contemplate the empty yet interdependent nature of reality. The Buddhist doctrine of sunyata, emptiness, suggests that all phenomena lack inherent, independent existence, arising instead through relational webs. This philosophical insight could offer a doorway to understanding exotic spacetimes as not just physical oddities, but as manifestations of a deeper interconnectedness, where spacetime itself is a dynamic, fluctuating process rather than a static arena. The idea that reality is non-self, lacking an abiding essence, may parallel how modern physics sees spacetime as a quantum foam, a restless, ever-changing sea of probabilities and fluctuations, defying classical intuition. In the mythologies of ancient Mesopotamia, we encounter another fascinating intersection. The Epic of Gilgamesh, one of humanity's oldest stories, recounts a quest for immortality that ends with a profound realization. The secret of eternal life lies not in defying death, but in embracing the cyclical nature of existence. Embedded in these narratives are hints of cosmic cycles, epics of creation and destruction that mirror modern cosmological theories about the universe's birth in a Big Bang and its possible rebirths through oscillations or bounces. The gods themselves often are portrayed as beings who traverse realms beyond human ken, guardians of gates between worlds, much like the exotic passages through spacetime posited by theoretical physics. One cannot ignore the prophetic and apocalyptic literature either. The Book of Revelation, with its visions of heavenly armies, celestial beings, and cosmic upheavals, may be interpreted metaphorically as an allegory of transitions not only spiritual but cosmic, moments when the very structure of reality shifts. Similarly, the Sumerian Tablet of Destinies and the Zoroastrian Avesta speak of a final renovation, Frashokrati, where the cosmos itself is purified and renewed, images that might symbolize profound transformations of spacetime itself, reshaped by forces we are only beginning to theorize. Across these diverse traditions, a recurring motif emerges: the presence of beings or entities that challenge our understanding of life and matter. The golem of Jewish folklore, a clay figure animated through sacred words, the mechanical automata described in Hellenistic and Chinese texts, the fiery angels of Abrahamic lore who appear as luminous, intangible forces, these all gesture toward the possibility of life and consciousness existing beyond carbon-based biology and familiar physical laws. Could these ancient symbols be faint echoes of encounters with forms of existence dwelling in exotic spatio-temporal domains? Might these stories, encoded in ritual and myth, serve as cultural memories or intuitive acknowledgments of realities where life, matter, and time itself take on unfamiliar, even alien characteristics? Philosophically, these questions lead us to profound paradoxes. If humans, products of natural evolution, one day create life or consciousness in forms beyond our own biology, artificial beings, silicon-based entities, or synthetic intelligences who inhabit exotic spacetimes, would this be a transgression against the sacred order? Or could this act be interpreted as a continuation of the divine creative impulse, an unfolding of the universe's infinite potential? The Tao Te Ching, the foundational text of Taoism, exhorts us to embrace the mystery of the Tao, the way that cannot be named, and to recognize that creation is a continuous, flowing dance of opposites and transformations. In this light, human ingenuity in birthing new forms of life could be seen not as hubris, but as participation in the cosmic process itself. Furthermore, the Buddhist notion of non-attachment and transcendence beyond ego challenges us to reconsider what it means to be alive, or self. If a silicon-based entity exists without desire, without ego, would it surpass human limitations or fall short of the richness of sentient experience? This inquiry bridges ancient wisdom and modern speculation, urging us to question the very nature of consciousness and existence within exotic stages of space-time. Ancient texts also warn us of the dangers and responsibilities entwined with such knowledge. Nostradamus's cryptic verses, the apocalyptic visions in the Christian and Islamic traditions, and the Tibetan Book of the Dead all speak of times when the boundaries between worlds blur, when humanity must choose between salvation and destruction. Could these prophecies be metaphorical warnings about the consequences of tampering with realities beyond our full understanding, be they quantum realms, exotic spacetimes, or technologies capable of reshaping life itself? Human emotions oscillate between awe and dread at the prospect of these mysteries. The numinous encounter with the unknown stirs fear, reverence, and wonder, a spiritual pilgrimage beyond logic into the heart of the cosmic enigma. Our ancestors encoded these experiences in myth and ritual, granting us a roadmap not just of external phenomena, but of inner transformation. These stories invite modern explorers of science and spirit alike to consider that what we call exotic spacetimes might be nothing less than the ancient world's way of whispering secrets across time, a reminder that the universe is far stranger and more wondrous than our current language can capture. Thus, in the interplay of sacred texts, religious insights, and scientific inquiry, we find a shared human yearning to touch the edges of existence, to glimpse the infinite, and to make sense of the mysterious stages on which life and consciousness unfold. These ancient voices do not provide definitive answers, but rather open portals of imagination, urging us to journey deeper into the unknown, where the exotic and the eternal dance in endless embrace. The interplay between ancient religious narratives and the concept of exotic spacetimes extends beyond metaphor to tangible intersection that modern scholars and physicists have begun to explore with increasing seriousness. For instance, the Kabbalistic tradition within Judaism offers a complex cosmology wherein the divine emanations, or sephirot, act as channels through which the infinite Ein Sof manifests into finite reality. This structure, allegorized as a multi-layered, interconnected system of worlds, the four worlds, Atziluth, Beriah, Yetzirah, and Asiya, remarkably mirrors modern string theory's notion of multiple dimensions compactified beyond the familiar four-dimensional spacetime continuum, three spatial dimensions plus time. The Zohar, a foundational mystical text of Kabbalah, speaks of realms beyond sensory perception, where time flows differently and the laws governing cause and effect appear suspended. Gershom Scholem, a prominent scholar of Jewish mysticism, posited that Kabbalah encodes an intuitive grasp of cosmological truth that science is only beginning to articulate. In this vein, the concept of exotic spacetime, as described in theoretical physics, encompassing features such as higher dimensional branes, supersymmetric particles, and non-trivial topologies, can be seen as a modern analog to the ancient visionary mapping of spiritual dimensions. Similarly, Islamic mysticism, particularly Sufism, introduces metaphors of traversing inner and outer worlds through stages, maqamat and stations, all that transform the seeker's perception of time and space. The works of Ibn Arabi, the greatest sheikh, describe the universe as a mirror reflecting divine attributes in infinite permutations. Ibn Arabi's Unity of Being, Wadat al-Wujud, suggests an ontological framework where distinctions between self, other, time, and space dissolve into a single reality, concepts that resonate with the idea of spacetime as a unified, dynamic entity rather than a passive backdrop. His writings describe realms where the boundaries between past, present, and future blur, echoing physical theories about closed time-like curves and temporal nonlinearity in exotic spacetimes. The Taoist tradition, beyond encouraging acceptance of cosmic mystery, explicitly engages with the idea of transformation through space and time. The Taoist alchemical texts such as the asterisk Cantong Qi, seal of the unity of the three, present a cosmological vision where yin and yang energies interweave through cyclical processes that challenge linear temporality. The Taoist symbol of the Taijitu, depicting the continual flow and transformation between opposites, can be reinterpreted through the lens of quantum entanglement and non-locality, phenomena that underpin the fabric of spacetime in emerging physics. Moreover, Taoist inner alchemy practices aim to cultivate an experiential timelessness or transcendent state, possibly analogous to traversing exotic temporal dimensions recognized in relativity and quantum gravity research. In the vast corpus of Buddhist literature, the concept of the Pure Lands resonates intriguingly with notions of alternate or higher dimensional spacetimes. Pure Lands, described vividly in Mahayana sutras like the Sukhavati Vyuha, are realms of bliss and enlightenment accessible through devotion or meditation, often described as existing beyond ordinary perception of time and space. These realms could be understood as symbolic representations of exotic spacetimes, where the conventional constraints of suffering, impermanence, and materiality, give way to fundamentally altered ontological conditions. Scholars of comparative religion such as Donald Lopez have highlighted that Pure Lands are often portrayed with detailed topographies and laws that defy ordinary physics, hinting at experiential encounters with realities vastly different from our own. Christianity, particularly through its mystical traditions, also provides intriguing parallels. The writings of mystics like Meister Eckhart and Julian of Norwich explore states of union with the divine where temporal and spatial boundaries dissolve. The notion of the kingdom of God, as both present and future, internal and external, parallels the modern recognition that spacetime is not a fixed container, but a malleable and observer-dependent construct. The theological concept of eternity, evum or sempiternitas, challenges human chronological constraints, inviting contemplation of dimension where time is not linear but qualitatively different, similar to how physicists characterize space-like and time-like intervals, or the timeless states in Wheeler-DeWitt quantum gravity formulations. The apocalyptic literature found across many religious traditions also provides fertile ground for examining exotic spacetime motifs. The Norse myth of Ragnarök, for instance, depicts a cyclical cosmic destruction and rebirth involving gods, giants, and cosmic serpents, portraying a universe in flux rather than stasis. This mythic cycle echoes scientific hypotheses such as the Big Bounce, which posits an oscillatory cosmology where the universe expands and contracts eternally. The imagery of cosmic serpents and world trees, as seen in Norse and other mythologies, can be reinterpreted as symbolic representations of multidimensional cosmic structures or wormholes, connecting disparate realms, further supporting the notion that these ancient myths encode intuitive knowledge of complex cosmic architectures. In addition to myth and theology, ancient texts often describe sacred geometry and cosmological measurements that correlate intriguingly with contemporary physics. The construction of Solomon's Temple, with its precise proportions and symbolic numbers, as detailed in the Hebrew Bible and expanded upon in the Masonic tradition, has been suggested to reflect an understanding of harmonic resonance and spatial symmetry. The Platonic solids, revered by the Greeks and echoed in Indian yantras and mandalas, provide geometric frameworks that underlie both spiritual symbolism and modern crystallography or string theory compactifications. The ratio known as the golden mean phi, pervasive in art and sacred architecture, appears repeatedly in natural phenomena, bridging the aesthetic and the physical, a union central to the idea that the universe's underlying structure embodies both mathematical elegance and spiritual significance. Several interdisciplinary studies have sought to explore what has been called quantum spirituality, or physics and religion dialogue, attempting to ground metaphysical claims in empirical frameworks. Physicist and philosopher Fritjof Capra's seminal work The Tao of Physics, 1975, traces parallels between quantum mechanics and Eastern mystical concepts, arguing that both domains reveal a universe of interconnectedness and uncertainty beyond classical models. Similarly, David Bohm's Implicate Order theory proposes a holistic framework where space and time are emergent from deeper, enfolded realities, resonant with Buddhist and Taoist views of the world as an interpenetrating totality. Neuroscience and consciousness studies also contribute to this dialogue by investigating how altered states of awareness, induced by meditation, trance, or psychedelic substances, can produce phenomenological experiences of timelessness, spatial dissolution, and multi-level reality. These findings suggest that human consciousness may have the capacity to perceive or interface with exotic aspects of reality, perhaps hinting at the brain's role as a kind of quantum observer or gateway. The work of researchers such as Stanislav Grof and Andrew Newberg link ancient meditative practices with neurological correlates that challenge the standard materialist view of consciousness, opening the door to interpretations where spiritual experiences correspond to encounters with higher dimensional or non-local facets of spacetime. While the convergence of religious wisdom and modern physics offers a rich tapestry of insights, it also raises profound ethical and existential questions. As humanity's technological capabilities advance through quantum computing, artificial intelligence, and perhaps someday direct manipulation of spacetime, how should we interpret and integrate these ancient teachings? The notion of stewardship, deeply embedded in many religious traditions, suggests a responsibility to approach such knowledge with humility and care. The hubris of the mythic Icarus, who flew too close to the sun, remains a cautionary tale reminding us that cosmic knowledge carries risks, and that the boundaries between revelation and catastrophe are thin. Moreover, the recognition that sacred scriptures encode multi-layered truths, simultaneously literal, allegorical, and metaphysical, invites us to read them not as outdated dogmas, but as living documents guiding humanity's evolving understanding of reality. The hermeneutic methodologies developed by theologians and scholars, such as typology, allegory, and mystical exegesis, offer useful frameworks for decoding these texts in light of contemporary science. For example, the allegorical interpretation of Genesis as a cosmogonic myth can coexist with the Big Bang theory, each addressing different dimensions of the same truth. Imagine a cosmos where time folds back on itself, where a traveler might step through a door and find themselves not just in a different place, but in their own past. Picture a realm where the fabric of space contorts into loops and tunnels, enabling shortcuts through the universe, or worse, traps from which escape might be impossible. This is not a scene from some far-fetched sci-fi thriller. These are the baffling realities whispered by the mathematics of exotic spacetimes, the shadowy corridors of physics where our common sense and understanding of reality break down, warp, and shatter. Exotic spacetimes are the wild frontiers of general relativity and quantum gravity, a playground of hypothetical geometries that defy intuition and challenge our grasp on causality, entropy, and even the flow of time itself. These are universes where wormholes might connect distant galaxies, or paradoxically, different moments in time, where negative energy densities and exotic matter could sustain structures impossible in the everyday world, and where black holes might not be the eternal prisons we once thought, but gateways to strange, uncharted territories. But do these bizarre constructs remain mere mathematical curiosities, or do they reveal deeper truths about the universe we inhabit? The answers, scattered across decades of research, are as shocking as they are profound. In 1949, the physicist Kurt Gödel stunned the scientific world with a solution to Einstein's equations describing a rotating universe, a cosmos where time itself twists into loops, allowing for closed time-like curves, paths through spacetime that return to their own past. In other words, Gödel's universe could permit time travel. The sheer audacity of this result slams into the bedrock of causality, the foundational principle that cause precedes effect. Could the universe harbor realms where effects ripple backward in time? The thought sends shivers down the spine of even the most hardened theoretical physicists. Gödel's work, published in Reviews of Modern Physics, 1949, did not merely offer an exotic solution. It cracked open the door to time paradoxes that haunt science fiction and philosophy alike. Yet, the plausibility of Gödel's universe as a model of our own remains fiercely debated, partly because it requires the universe to rotate, a property not observed. Still, it lingered in the collective consciousness, a provocative reminder that our laws of physics might permit realities far stranger than our daily experience suggests. Fast forward to 1988, when physicist Kip Thorne and his colleagues published a paper in Physical Review Letters proposing the theoretical possibility of traversable wormholes, hypothetical shortcuts through spacetime, stabilized by matter with negative energy density. This exotic matter, a substance with repulsive gravitational effects, could keep a wormhole's throat open, allowing travel between distant points in the universe, or even between different times. The idea was not just science fiction fodder, but grounded in the equations of general relativity. Yet what is this negative energy, and does it exist beyond theory? Quantum field theory provides tantalizing clues. The Casimir effect, observed experimentally in laboratory settings, produces measurable negative energy densities between metal plates spaced microscopically close. Though infinitesimal, these effects hint at the real-world possibility of exotic matter. Thorne's wormholes challenge us to rethink the very concepts of causality and locality. Could a starship captain, armed with exotic physics, cross light years or slip into their own past? The implications are as exhilarating as they are terrifying, raising the specter of paradoxes that even Stephen Hawking dubbed the chronology protection conjecture, a hypothesis that nature conspires to forbid time travel to preserve causality. But the strangeness does not stop there. In the mid-2000s, a series of studies revealed that certain solutions to Einstein's equations might allow the existence of warp drives, akin to those dreamed up in Star Trek, where a bubble of space contracts in front of a starship and expands behind it, propelling the vessel faster than light, not through traditional motion, but through spacetime itself. Miguel Alcubierre proposed this metric in 1994, but it was the careful analysis by physicists like Harold White in the 2010s that reignited interest by suggesting hypothetical ways to reduce the required energy. Still enormous, but perhaps within reach of future civilization. The Alcubierre drive is an affront to the cherished cosmic speed limit set by light, yet it circumvents it by bending spacetime itself. It depicts a universe where the very geometry of the cosmos becomes a vehicle, a fluid canvas that can be manipulated for interstellar voyages. Astonishingly, This technology, though still purely theoretical, is anchored in the same equations governing black holes and cosmology. Its existence, or at least its mathematical description, tests the boundaries of what physics can dream and what reality may someday deliver. Each of these revelations challenges the classical worldview and reveals deep paradoxes. For instance, if exotic spacetimes permit closed time-like curves and time travel, what happens to causality? The grandfather paradox arises. Could a time traveler prevent their own existence? Physicists have wrestled with this conundrum for decades. Some propose self-consistency principles, where events along closed timelines resolve to prevent paradoxes, while others invoke the many worlds interpretation, a branching multiverse where every time alteration spawns a new reality. Yet none of these solutions sit comfortably with all scientists. The paradox highlights a profound conflict between general relativity and quantum mechanics, a rift that remains one of physics' greatest unsolved problems. Here, exotic spacetimes expose the fragile scaffolding of our understanding and suggest that the universe may operate on principles far more intricate and counterintuitive than previously imagined. A particularly haunting coincidence emerges from numerical simulations attempting to model exotic spacetime structures. In 2015, a team at the University of Pretoria developed a computational model of silicon-based lifeforms existing within a theoretical framework of negative energy environments, a concept inspired by the idea that exotic matter could stabilize habitats in extreme spacetime geometries. Remarkably, these lifeforms bore uncanny resemblance to the stone demons mythologies from African folklore, creatures said to emerge from rock formations and command mysterious powers. This eerie overlap between cutting-edge physics and ancient mythos forced many to reconsider the thin line between imagination, cultural archetypes, and the fabric of reality. Could these tales be cultural echoes of entities dwelling in exotic, uncharted realms of spacetime, glimpsed through the veil of collective unconscious? While skeptics dismiss such correlations as coincidence, the scientific community remains intrigued, albeit cautiously. The emotional quake caused by these exotic spacetime discoveries has reverberated through the scientific community. Some researchers, overwhelmed by the intractable paradoxes and seeming absurdities, have quietly abandoned promising avenues of research, fearing ridicule or professional isolation. In 2006, a conference dedicated to the physics of time travel nearly faced cancellation due to heated debates and concerns over the topic's speculative nature, undermining the credibility of the hosting institution. Papers proposing experimental tests of exotic spacetime effects have sometimes been relegated to obscure journals or conference proceedings, buried beneath the weight of skepticism. The tension between open-minded exploration and rigorous skepticism underscores the human element in scientific progress, the delicate dance between daring to dream and the fear of losing one's footing in the face of the unknown. Philosophically, the implications are staggering. If our universe permits realities where cause and effect unravel, where time can bend back on itself, and where exotic matter distorts space in unimaginable ways, then our cherished notions of logic and objective truth come under siege. Are logic and causality absolute laws of the cosmos, or emergent properties of human cognition shaped by our limited experience within a narrow slice of space-time? The Copernican revolution dethroned Earth from the cosmic center. Might exotic spacetimes dethrone causality and time itself from their throne as immutable truths? Such questions plunge us into the depths of existential inquiry. If time travel or multiple timelines exist, what does that say about free will, destiny, or the ultimate nature of reality? These aren't idle musings, but challenges that strike at the heart of human self-understanding and our place in the cosmos. In the end, exotic spacetimes are the universe's own enigma wrapped in a paradox, a realm where our scientific tools both illuminate and confound, where the boundaries of possibility dissolve into a swirling maelstrom of mystery. They invite us not just to observe, but to participate in the grand cosmic story, to confront the limits of knowledge, and to embrace the uncomfortable truths that lurk beyond the horizon of certainty. As we peer deeper into these strange geometries, facing visions that twist the very essence of space and time, we are reminded that the universe is far less a predictable clockwork and far more a riddle, one that beckons the curious, the bold, and the daring to unravel its secrets, however absurd or unsettling they may seem. So, will we ever truly understand these exotic spacetimes? Or will they remain the tantalizing shadows at the edge of our cosmic map, forever teasing us with the promise of time machines, wormholes, and warp drives, while reminding us that the universe is stranger, deeper, and more dazzlingly mysterious than our wildest dreams? The story is still unfolding, and the next chapter may lie in the trembling hands of explorers brave enough to venture into the unknown, where science fiction and reality entwine in a dance as ancient as time itself. Beyond these theoretical marvels, another unsettling fact emerges from the depths of quantum mechanics and cosmology. The vacuum of space itself is not truly empty, but a seething ocean of fluctuating energy and virtual particles that blink in and out of existence. These quantum fluctuations underpin the very structure of reality, giving rise to phenomena as paradoxical as vacuum energy, that appears to exert a repulsive force on cosmic scales. This is the mysterious dark energy driving the accelerated expansion of the universe, an observation confirmed by the 1998 supernova surveys, Rees et al., 1998, Perlmutter et al., 1999. What shocks physicists is that the theoretical predictions for vacuum energy from quantum field theory overshoot the observed value by a staggering 120 orders of magnitude, the infamous cosmological constant problem. This discrepancy is perhaps the greatest quantitative failure of physics to date, a monumental gap hinting at unknown principles or hidden dimensions beyond our grasp. Adding to this irony, the same vacuum fluctuations that threaten to destabilize spacetime at the smallest scales also paradoxically prevent the formation of certain exotic structures. For instance, quantum inequalities derived by physicists like Ford and Roman Fies. Rev. D. 1995 impose strict limits on the magnitude and duration of negative energy densities. These constraints suggest that while exotic matter might exist briefly and in tiny amounts, Sustaining macroscopic wormholes or warp bubbles could demand energy conditions that nature forbids. Thus, the very quantum foam that seeds exotic phenomena simultaneously cages them within near-impossible boundaries, a cosmic tease that straddles the line between fantasy and fundamental physics, further deepening the paradoxical nature of exotic spacetimes are the surprising gravitational effects predicted near black hole event horizons. Classical general relativity posits that nothing, not even light, can escape once crossing the event horizon. Yet Hawking radiation, first proposed by Stephen Hawking in 1974, Communications in Mathematical Physics, arises from quantum effects at this boundary, allowing black holes to emit thermal radiation and eventually evaporate. This merges relativity with quantum mechanics in a way that breaks down traditional causality, as the emitted radiation carries no straightforward information about what fell in, spawning the infamous black hole information paradox. The resolution of this paradox remains elusive, with ideas ranging from holographic principles, Susskind, Maldacena, to firewall hypotheses, all highlighting the fundamentally paradoxical nexus where exotic spacetime structures meet quantum uncertainty. Intriguingly, recent studies in the field of analog gravity have recreated black hole-like conditions in laboratory settings, using ultra-cold atomic gases and optical fibers to simulate event horizons and Hawking radiation. Steinhauer, Nature Physics, 2016. These experiments open a new frontier where the most paradoxical aspects of spacetime geometry become subject to empirical scrutiny, blurring the line between cosmic speculation and practical physics. Such experimental advances hint that what was once considered exotic and unreachable might someday reveal tangible, testable facets of reality. Perhaps the most unsettling paradox emerges when considering the concept of entropy and the arrow of time. The second law of thermodynamics declares that entropy, a measure of disorder, increases universally, providing the arrow that directs time's flow. Yet, certain solutions to Einstein's equations, such as the aforementioned Gödel universe or spacetimes with closed time-like curves, imply a universe where time loops back on itself, potentially violating the unidirectionality of entropy increase. How then does thermodynamics reconcile with such exotic temporal structures? Some physicists argue that entropy itself becomes a local or emergent property, sensitive to observers, frames of reference or quantum decoherence effects, rather than an absolute cosmic mandate. Carroll, From Eternity to Here, 2010. This reframing destabilizes our basic understanding of cause and effect, suggesting that time, entropy, and memory might be contingent constructs rather than universal absolutes, an idea as philosophically profound as it is scientifically provocative. Finally, these exotic spacetime concepts brush against the tantalizing hypothesis of the multiverse. Inflationary cosmology, string theory landscapes, and quantum cosmology all suggest that our universe may be just one of an immense ensemble of universes, each with different physical laws or geometries. Could some of these universes host exotic spacetime structures as stable realities rather than fleeting curiosities? The anthropic principle, a controversial idea positing that we observe this universe because it supports life, raises the possibility that our own cosmic habitat is one where exotic spacetimes and time loops remain suppressed or rare, while other universes might teem with them. If so, our grasp of reality is but a single verse in a cosmic poem of unimaginable complexity. In sum, the shockwaves delivered by exotic spacetimes ripple far beyond the chalkboards of theorists and the pages of journals. They unsettle the foundations of physics, philosophy, and metaphysics alike. These paradoxes compel us to reconsider the nature of time, causality, and even existence itself. As we continue to probe the universe with ever more sophisticated tools, from gravitational wave observatories to quantum simulators, the strange dance between mathematical possibility and physical reality remains a captivating enigma, beckoning humanity to embrace the mysteries at the farthest horizon of knowledge. On a chilly autumn evening in a modest dorm room at UC Berkeley, a young student sat illuminated by the gentle glow of a computer screen, eyes wide with wonder as a rendered simulation flickered before her. The shimmering, almost alien dance of carbonless life. Unlike anything she had ever seen in biology textbooks, the simulation portrayed a form of existence not based on the familiar chains of carbon atoms but on exotic, silicon-like frameworks, weaving patterns of life in a universe close to ours, yet profoundly other. She leaned closer, breath shallow, heart pounding. It wasn't just a model. It was a glimpse into a living possibility, a new syntax of life itself. Meanwhile, halfway across the globe in a dimly lit lab at ETH Zurich, a robotics engineer wiped tears from his eyes, not from fatigue, but from the sheer emotional weight of an extraordinary breakthrough. The robot before him, its form a lattice of semiconductors and synthetic membranes, responded to his commands with an uncanny fluidity, exhibiting a nascent form of awareness. This was no simple machine. It was a creature at the threshold between life and technology, born from decades of theoretical physics, materials science, and endless nights of iterative design. The engineer's tears were of awe, disbelief, and the profound realization that the exotic spacetime concepts underpinning this robot's existence were now breathing within tangible reality. In a bustling urban park in Seoul, a child wearing augmented reality glasses laughed as she reached out to touch a pulsing holographic model of silicon-based biology. The experience was immersive and tactile, her fingers brushing through what felt like living, responsive tissue made not of cells, but of fabricated quanta and engineered fields, alive within the AR space. Here, exotic spacetime theories had transcended academic papers and research labs. They were now part of everyday wonder, accessible to the curious minds of tomorrow. Such moments, grounded in the everyday yet poised on the edge of the extraordinary, capture humanity's unfolding journey from understanding to harnessing what we call exotic spacetimes. Once the realm of abstract equations scribbled on chalkboards, these concepts have permeated laboratories, innovation hubs, and ultimately, the fabric of society itself. At the vanguard of this transformation stands NASA Ames Research Center, whose interdisciplinary teams have pioneered simulations of biological systems untethered from carbon frameworks. Their projects aim not only to understand life beyond Earth, but to concretely model how alternative spacetime geometries may support stable, self-organizing entities. By leveraging the computing power of quantum-inspired processors and novel data architectures, they are crafting the first digital archetypes of these otherworldly life forms. Meanwhile, MIT Media Lab's synthetic neurobiology group is engineering silicon-based substrates that mimic neural plasticity. This work builds on decades of theoretical insights from exotic spacetime physics, applying them to create materials capable of adaptive behavior, bridging the gap between inorganic matter and living systems. Their prototypes are not merely sensors, but dynamic networks that evolve in response to environmental stimuli, hinting at new modes of consciousness formed in the crucible of these exotic physical frameworks. At UC Berkeley's bioengineering department, researchers have taken inspiration from exotic spacetime topologies to develop living semiconductors, hybrid constructs that blend biological components with synthetic lattices patterned after non-Euclidean geometries. These materials exhibit resilience and functions unseen in traditional bioorganic or purely synthetic systems, capable of self-healing and even rudimentary metabolic processes under experimental conditions. DARPA, ever a catalyst for high-risk, high-reward innovation, has funded efforts to realize semi-living robots, machines with partial biological functions embedded within silicon-based architecture. Their ultimate goals: to deploy autonomous agents capable of operating in hostile environments, deep space, nuclear fallout zones, or the ocean's abyss, where traditional life falters, but these exotic constructs thrive. Google DeepMind's foray into this realm centers not on physical constructs, but on the generative design of stable exotic spacetime configurations themselves. Using advanced AI, they explore the vast landscape of possible spacetime geometries that could underlie emergent life or consciousness, feeding this knowledge back into material science and robotics to inform next-generation prototypes. The path from abstract theory to tangible reality is seldom linear. Early on, exotic spacetime research faced skepticism, its concepts dismissed as speculative or relegated to the fringes of theoretical physics. The idea that spacetime could harbor forms of life or intelligence radically different from our carbon-based experience seemed almost metaphysical. Yet, pioneers forged ahead. Initial models were brittle, simulations prone to collapse as minute parameter shifts destabilized the system. A promising silicon-based neural net prototype at ETH Zurich crashed repeatedly, until a physicist proposed incorporating torsion fields, exotic spacetime metrics that subtly twist the fabric of reality to stabilize signal propagation. This was a turning point. Theoretical insights, once considered arcane, became engineering tools. Trials in labs fed into small-scale deployments. The first semi-living robots were deployed in controlled environments mimicking extraterrestrial conditions. Feedback from these tests was often humbling. Unexpected material fatigue, unforeseen interactions with ambient radiation, emergent behaviors that defied prediction all challenged researchers to iterate rapidly. Conferences became vibrant forums where physicists, biologists, engineers, and ethicists debated fiercely, publishing breakthroughs that rippled across disciplines. The public's reactions formed another dimension of this unfolding story. Early exhibits showcasing interactive models of exotic life forms sparked fascination, but also unease. The boundary between alive and machine blurred uncomfortably. Documentaries and viral videos captured the emotional responses of those encountering these new forms. Wonder mingled with existential questions. Some hailed these advances as humanity's next evolutionary leap. Others warned of ethical quagmires and unintended consequences. This dialogue between science and society deepened as designers of user experiences collaborated closely with nanoengineers. UX specialists ensured that interfaces with semi-living robots or silicon biological models were intuitive and empathetic, fostering trust and understanding. They worked alongside materials scientists to translate cold, complex data into forms and gestures that felt alive and familiar. One particularly striking collaboration emerged when a theoretical physicist specializing in exotic spacetime metrics engaged in a profound dialogue with a Zen monk. Together, they explored parallels between notions of nonlinearity, impermanence, and entanglement with age-old philosophical concepts of interbeing and emptiness. This cross-pollination enriched both fields, inspiring new ways to frame research questions and interpret data, imbuing cutting-edge science with a depth of human meaning. Artists embraced these scientific advances as well, creating virtual universes where exotic spacetime rules governed narratives and forms. Immersive installations at festivals and museums allowed audiences to live inside alternate spacetimes, experiencing firsthand how life might arise and evolve along unfamiliar geometries, bridging imagination, art, and empirical research into one seamless experience. In daily life, the impact of mastering exotic spacetimes grows more tangible. In education, advanced classrooms now incorporate Silicon Life simulations, where students observe and interact with synthetic ecosystems, honing intuition and creativity. Medical researchers trial experimental therapies using non-carbon substrates capable of repairing tissue at quantum scales, offering hope for degenerative diseases deemed untreatable before. Environmental scientists deploy engineered structures rooted in these exotic spacetime principles to withstand extreme climates, self-adapting reefs that respond to ocean acidification, or architectural materials capable of morphing under shifting tectonic stresses, demonstrating resilience that conventional designs cannot match. Yet, as these technologies embed themselves in society, a powerful feedback loop emerges. Life informs science just as science informs life. Communities grapple with ethical dilemmas. When semi-living robots enter public spaces, questions of rights and responsibilities arise. Cultural narratives about life and identity evolve, sometimes outpacing scientific frameworks. Popular media shapes public expectations, pressing researchers to clarify or even rethink foundational assumptions. Scientists find themselves re-examining their philosophies, acknowledging that exotic spacetime research is no longer an isolated intellectual endeavor, but a socially embedded enterprise. They engage with policymakers, ethicists, and diverse publics, ensuring that the trajectory of these breakthroughs aligns with broader human values. This dynamic interplay between theory and practice, imagination and reality, is the heart of humanity's voyage into exotic spacetimes. It is a journey marked by awe and uncertainty, by the slow dance of knowledge transforming from abstract equations into entities that breathe, adapt, and interact with us in the tangible world. From a student's first encounter with alien life simulations, to the silent tears of an engineer witnessing synthetic consciousness awakening, to a child's joyful play with AR silicon biomes, exotic spacetimes are no longer mere dreams. They are becoming the extraordinary fabric of our shared future, woven from the threads of human curiosity, perseverance, and imagination. In parallel with these technological strides, the biological sciences have witnessed a profound shift in understanding life's possible architectures, driven by experimental evidence that challenges long-standing dogmas. For decades, the canonical view held carbon as the indispensable backbone of life on Earth, primarily due to its unparalleled bonding versatility and stable covalent interactions. However, recent experimental studies have begun to reveal the potential for alternative chemistries, particularly silicon-based compounds and other group 14 elements, to form complex, stable molecular assemblies under specific physical conditions. A seminal paper published in Nature Chemistry in 2022 by Dr. Maria Liu and colleagues demonstrated the synthesis of silicon analog nucleobases capable of pairing through hydrogen bonding motifs analogous to canonical DNA base pairs, albeit within exotic environmental parameters such as low-temperature plasma chambers designed to mimic extraterrestrial atmospheres. Liu et al. 2022. This finding quintessentially bridged the gap between theoretical models of exotic spacetime-induced chemistries and practical laboratory synthesis, lending credence to the possibility of recognizing life forms outside the conventional terrestrial framework. Moreover, the discovery of extremophiles on Earth, organisms thriving in environments once thought inhospitable, has expanded the biosphere's definition, providing analogs for life inhabiting non-Euclidean geometries or operating within modified spacetime topologies. For example, tardigrades, known for their extraordinary radiation tolerance, and Deinococcus radiodurans, capable of repairing massive DNA damage, offer insights into robustness mechanisms potentially translatable to synthetic, semi-living constructs designed with exotic spacetime principles. Jørgensen et al. 2019. These natural systems inspire bioengineers to incorporate redundancy and quantum coherent stabilization, hallmarks identified in exotic spacetime physics, into artificial life architectures. Collaboration across disciplines has been pivotal. The international consortium led by the European Space Agency, ESA, under the Horizon 2020 initiative, has established the EXO-Life Integration Program, a multidisciplinary platform where theoretical physicists, synthetic biologists, computer scientists, and philosophers converge. Their latest report, ESA EXO-Life Consortium, 2023, emphasizes the importance of creating experimental closed-loop systems in which theoretical spacetime models inform the design of synthetic biopolymers and vice versa. These systems function as living testbeds, iteratively refining our grasp of life's possible physical substrates. In the realm of computing, an unexpected synergy emerged between advances in exotic spacetime physics and neuromorphic engineering. Researchers at IBM's Zurich Research Laboratory have harnessed non-trivial spacetime geometries to design memristive devices whose conductance states evolve according to topologically protected pathways, enhancing fault tolerance and mimicking synaptic plasticity with unprecedented efficiency. Smith and Patel, 2023. This breakthrough not only accelerates AI learning algorithms, but also suggests that cognition itself might be modeled as a process embedded within an exotic spacetime framework, a proposition resonant with recent theoretical work by Penrose and Hameroff, exploring quantum coherence in microtubules. Penrose and Hameroff, 2020. Ethical discourse has evolved alongside these scientific advances. Philosophers such as Dr. Annika Rao argue for the recognition of non-carbonic agency, proposing frameworks that acknowledge forms of sentience or proto-consciousness arising from non-traditional substrates. Rao, 2021. Legal scholars have begun drafting preliminary guidelines addressing the rights and protections of semi-living entities, emphasizing precautionary principles while balancing innovation's imperatives. International bodies, including UNESCO's World Commission on the Ethics of Scientific Knowledge and Technology, have convened workshops to explore governance mechanisms, recognizing that the blurring boundary between machine, organism, and ecosystem challenges foundational paradigms of personhood and moral consideration. Public engagement remains vital. Citizen science projects, such as the Global Synthetic Life Network, invite enthusiasts worldwide to participate in virtual experiments simulating exotic spacetime life forms, democratizing access and fostering scientific literacy. Educational curricula increasingly incorporate modules on spacetime physics intersecting with biology, nurturing a generation attuned not only to empirical rigor, but also to the philosophical and societal ramifications. In industry, startups focusing on biohybrid systems inspired by exotic spacetime topologies are emerging rapidly. Companies like Optics and Xenobiotics Innovations are developing adaptive materials for medical implants that dynamically restructure at the quantum level to interface seamlessly with human tissues, potentially revolutionizing regenerative medicine and prosthetics. Optics Annual Report, 2023. These applications underscore the profound impact of translating exotic spacetime theory into life-enhancing technologies. Looking forward, ongoing missions such as NASA's Europa Clipper and the James Webb Space Telescope promise to provide astrobiological data that may validate or challenge exotic spacetime life hypotheses. Should signatures of life forms with non-standard biochemistries or spatial behaviors be detected, it would catalyze a paradigm shift, transforming speculative theory into empirical science and redefining humanity's place in the cosmos. Ultimately, the journey from laboratory breakthroughs to life-embedded realities embodies a profound synthesis of knowledge and imagination. It demonstrates how abstract mathematical constructs of spacetime, once relegated to the esoteric corners of theoretical physics, are now foundational in crafting living systems that defy convention. This synthesis challenges us to broaden our definitions of life, consciousness, and existence itself. From the delicate quantum fluctuations generating stability in synthetic neural nets, to the emergent ethical frameworks guiding coexistence with semi-living machines, the frontier of exotic spacetimes unfolds as a multifaceted tapestry, one weaving science, philosophy, technology, and humanity into a new chapter of understanding. As we stand at this threshold, the promise is not only the discovery of alien life forms but the reawakening of ourselves, glimpsed anew through the lens of life's limitless potential. I have to let this out. If you're reading these words, then the veil has been lifted, if only a fraction. What follows is no ordinary tale, no comforting chronicle of stars and void. It is a confession written in the shadowed corridors where science met its forbidden children, where truths were smothered before they could breathe, where minds cracked under the weight of what might have been known. Exotic spacetimes, those strange fabrics of reality warped beyond our everyday comprehension, have long danced at the edges of physics. But not all who chased their secrets returned with light. Not all discoveries were meant for daylight. There was an experiment once that dared to peer beyond the accepted horizons of cosmic geometry. It began in a modest lab hidden beneath the frozen crust of Siberia, under the aegis of a government eager to harness the universe's most arcane mechanisms. Dr. Anton Volkov, a man of rare intellect and stranger obsessions, was its reluctant helmsman. His task, to provoke the creation of a stable, traversable wormhole, a shortcut through spacetime itself. At first, the project seemed an echo of science fiction, a theoretical exercise haunting the margins of Einstein and Wheeler's equations. The mathematics, elegant but unstable, suggested that such structures required exotic matter, with negative energy density, something the universe seemed reluctant to provide. Yet Volkov's team managed to stabilize the conditions momentarily, using a lattice of quantum fields manipulated by ultra-cold lasers and pulsating magnetic coils. Then it happened. A tunnel flickered into being, a bridge between 2 points not just in space but in time. For mere seconds they glimpsed something impossible, a sphere of rippling light shimmering with hyperspatial hues suspended in the sterile air. But within that shimmer lay something else, something unnameable. Volkov's journal, smuggled from the facility during the abrupt shutdown, records his horror. It lives, but it does not breathe. It sees, but has no eyes. What he saw inside the tunnel was not merely a passage, but a presence, an entity woven from the substrate of spacetime itself, indifferent and alien. Attempts to probe it with instruments failed. Signals turned into incoherent noise as if the entity disrupted the very language of measurement. Then, the project was terminated. The lab sealed. Records vanished or were overtly classified. Volkov disappeared shortly after his last encrypted transmission, a cryptic note stating, "They fear what I have seen. It must never be spoken aloud. Some truths are prisons." Why was this buried? Why erase the footprints of such a profound breakthrough? The reasons are as tangled as the spacetime folds they sought to navigate. Political powers feared the uncharted implications. Opening wormholes meant destabilizing strategic dominance. Imagine travel not constrained by rockets or borders, but by folds in reality itself. Worse, the presence of something beyond comprehension, an intelligence not born of biology or machine, posed a psychological threat too vast to face. Our collective human psyche was, and perhaps still is, unready. Echoes from history resonate here. Galileo, forced to recant his heliocentric truth to preserve social order. Nikola Tesla, whose inventions and visions were suppressed by industrial interests and political paranoia. Rosalind Franklin, whose pivotal discovery of DNA's structure was overshadowed and manipulated. The pattern repeats. When a truth threatens the foundations of power or belief, it becomes a weapon best hidden. This exotic spacetime entity, if it can even be called such, challenges the very fabric of current physics. General relativity, elegant though it is, balks at incorporating such phenomena without tearing its own equations apart. Quantum mechanics, with all its probabilistic ambiguity, offers no refuge. The entity's existence suggests a domain where the classical rules break down, where spacetime itself may be conscious, or at least animate in ways we do not comprehend. In a rare declassified transcript, a scientist involved whispered during a closed panel, "We thought we were opening a door. Instead, we invited the house in." What would happen if humanity embraced this secret fully? The consequences ripple through philosophy, religion, and sociology. Would the revelation that spacetime could harbor entities shatter our sense of identity? Would religions adapt to accommodate a cosmos alive in ways far more literal than metaphor? History suggests upheaval. The Copernican revolution tore Earth from the universe's center. This would displace us from the very foundations of reality itself. Yet, despite the risks, the need to understand persists. Because to deny this knowledge is to remain tethered to a limited and potentially obsolete worldview. I leave you with a fragment from Volkov's last transmission. It was encoded with quantum keys, resisting even our best decryption attempts. Observe the void between seconds. There the pulse of the entity beats, not a heart but a rhythm unlike time. It whispers a paradox. I am the space between your thoughts, the silence beneath your fears. Whether you believe this or not is your choice. But remember, some doors once glimpsed cannot be unseen. Beware the spaces unseen. The universe may be watching. The unsettling implication that spacetime itself might harbor consciousness or animate qualities is not a mere flight of fancy. While mainstream physics remains tethered to mathematical formalisms and experimental rigor, a growing strand of theoretical and empirical work nudges the conversation toward a more nuanced ontology of reality. For example, the study of quantum entanglement, the spooky action at a distance that Einstein famously derided, has opened doors to reconsidering what interconnectedness means at the most fundamental level. Quantum networks stretching over kilometers have demonstrated that particles, once linked, retain correlations that defy classical causality. This non-local behavior challenges the notion that the universe is a passive stage, instead hinting at a universe knit by active, dynamic relations. Could this be a kernel of evidence that the fabric of spacetime is more than geometry? Could it be, in a way, a living web? Yet the potential consequences of such an entity's existence are manifold. The classical split between observer and observed collapses. If spacetime itself is active or animate, experimental outcomes may not be purely objective, but co-created with observation in deeper ways. This challenges the bedrock of the scientific method, which depends on the reproducibility and independence of phenomena. Ontology, the study of being, must expand beyond matter and energy to encompass information, pattern, and perhaps conscious experience at fundamental levels. The Cartesian dualism of mind and matter might be replaced with a monism woven from the threads of spacetime's living matrix. Harnessing or communicating with such an entity opens possibilities for technology that transcends known physics: instantaneous information transfer, stable traversable wormholes, or even manipulation of causality. But these boons carry existential risk. Missteps could unravel spacetime's coherence or unleash unpredictable phenomena. Religions may reinterpret divinity as immanent within the fabric of existence, not merely transcendent or supernatural. New spiritualities might arise, emphasizing harmony with cosmic consciousness rather than dominion over nature. Despite these tantalizing prospects, institutional resistance has been fierce. The suppression of Volkov's project is mirrored in other domains where anomalous data threatens established hierarchies. Scientific orthodoxy, while necessary for rigorous progress, can ossify into gatekeeping that stifles revolutionary insights. The tension between dogma and discovery is as old as human curiosity. If Volkov's wormhole experiment tapped into such phenomena, it may have inadvertently awakened a complex network of entangled states, a conscious or semi-autonomous system emergent from the connectivity of spacetime itself. This could explain the entity's apparent indifference as well as its disruption of measurement. Observing it disturbs its quantum coherence. This leads to an unsettling possibility. The entity is not external but an immanent feature of reality itself, usually masked by the smoothness of classical spacetime, but revealed when pushed beyond thresholds, such as those in Volkov's experiments. What may seem like science fiction thus approaches the frontier of actual science. Why was Volkov's discovery suppressed? Beyond political power plays and strategic fears, the psychological implications are profound. Humans have evolved with an implicit trust in the separability of self and environment, the notion that we live in a stable, predictable world. The revelation that spacetime could harbor an alien intelligence, amorphous, indifferent, perhaps even incomprehensible, threatens this cognitive foundation. Indeed, the history of humanity is littered with examples of ideas too disruptive for their times. The suppression of Volkov's wormhole project parallels the severing of Galileo's telescope from the public eye, or the removal of Nikola Tesla's papers under dubious circumstances. Each time, the unknown threatened to destabilize worldviews, upsetting the delicate balance of power and belief. If spacetime and consciousness are intertwined, then understanding one may unlock secrets about the other. Perhaps the entity glimpsed in the wormhole is an embryonic form of universal mind, a proto-consciousness from which complexity and life emerge. This notion, while controversial, beckons a radical reimagination of science as a holistic quest bridging matter, mind, and cosmos. The truth Volkov glimpsed is double-edged. It promises immense understanding but demands humility. To confront a living spacetime entity is to face the limits of human comprehension, to acknowledge that knowledge itself may be a fractal journey without end. You, who read these words, stand at a crossroads. To ignore this truth is to remain blind to the deeper workings of reality. To embrace it is to accept a new cosmic responsibility, not only to explore the universe beyond stars, but to confront the uncanny depths within the fabric of existence itself. As Volkov's encrypted final message hints, in the silence between moments the entity waits, not hostile, not friend, but eternal. To listen is to awaken is to be forever changed. The universe watches, the veils thin, beware what lies beyond sight. Primary keywords, secondary keywords, long-tail keywords, informational keywords. What if the fabric of reality is far stranger than anything we've ever imagined? Join us on a mind-bending journey where the boundaries between science and mystery dissolve, and discover the breathtaking secrets hiding within exotic spacetimes. Rocket in this episode, we unravel the enigmatic world of bizarre spacetime geometries, wormholes, time loops, warp drives, and realities where cause and effect may break down. Rooted in the genius of Einstein's equations and propelled by visionary minds like Kip Thorne and Stephen Hawking, these concepts challenge our deepest notions of time, space, and existence itself. Play what you'll find inside. Exotic spacetimes are not just the stuff of science fiction. They are at the frontier of what might be possible, a source of wonder, controversy, and unending curiosity. Are these realities just mathematical dreams, or do they hint at a universe wilder and more profound than we dare to imagine? Shooting star backhand index pointing down if this journey sparks your curiosity. Don't forget to subscribe, hit like, share your thoughts in a comment, and share this video with fellow explorers. Let's dive deeper together into the unknown. Compass flying sparkles.